Muy buenas noches, chicos y chicas. Hola, ¿qué tal? Muy buenas noches. ¿Estamos en directo? ¿Estamos en directo? Sí, no, estamos en directo. ¿Me confirmáis que se ve, que se oye como debe de ser? ¿Estamos en directo? Muy buenas noches, chicos y chicas. Bienvenidos a DOTCSV versión nocturna, versión ASMR. ¿Se escucha bien? ¿Se me oye bien? Confirmadme, chat, os estoy leyendo. Perfecto, soy un poco la música de fondo, está muy alta, está bajita. Voy a bajar un poquillo. Bueno, chicos, bienvenidos. Estoy hablando un poco más bajo porque aquí me imagino que la gran mayoría de los que estáis conectados ahora mismo sois de Latinoamérica. Habrá unos cuantos locos de España, obviamente, aquí estamos también apoyando. Pero aquí son las 3 de la mañana. Y como son las 3 de la mañana y mis vecinos pues están durmiendo, pues vamos a hacer la labor de intentar comunicar, de hablar todo esto, pero sin levantar muchísimo la voz. Esto va a ser versión ASMR, ¿vale? Yo me acercaré al micrófono y estaremos susurrando, pero bueno. A ver, tampoco va a ser tan ASMR, ¿vale? Tranquilos, tranquilos. Bueno, bienvenidos a este evento tan especial, a este evento donde se fusiona la inteligencia artificial y el carisma del señor Elon Musk, como ocurre justo en esta foto con mi cara y la cara de Elon. Bueno, generada con Stable Diffusion, ya sabéis que es mi último juguete que no paro de utilizar. Aquí podéis ver más resultados. Esto es lo que sería el resultado de si yo hubiera sido millonario, multimillonario. En esto me hubiera convertido. No sé si realmente me vale con quién soy ahora mismo. Pero bueno, estamos hoy reunidos aquí porque se va a celebrar el Tesla AI Day. Joder, es que son muy buenas las imágenes, ¿eh? Mirad esta. Terrorífica. ¿Vale? Espectacular. Estamos hoy aquí porque en cuestión de 12 minutos comienza el Tesla AI Day. ¿Qué es esto? Bueno, el Tesla AI Day es el evento anual, el segundo que se celebra, de hecho, oficial, dicho por Nvidia, de inteligencia artificial. Es decir, es un evento que que Tesla celebra para demostrar, contar al mundo todas las novedades que tienen, que han desarrollado en el campo de la inteligencia artificial. Y no es un evento pensado para el marketing. Estaba leyendo en el chat gente que comentaba que bueno, que Elon Musk al final es un poco... Dios. Que Elon Musk es una persona, bueno, pues que tira mucho del marketing, que vende mucho humo, que no... bueno, que exagera, ¿no? Y sabemos que esa es una de las dimensiones del señor Elon Musk, pero hay que decir que para mí el evento que vamos a ver hoy, al menos el año pasado, fue uno de los mejores eventos técnicos que nunca he visto. O sea, es una cosa espectacular. Es una cosa espectacular, ¿vale? Y además este año puede que sea especialmente interesante porque no solo veremos novedades en cómo funciona su sistema Autopilot, ya sabemos su sistema de conducción autónoma que tiene en los vehículos de la empresa de Tesla. No solo veremos novedades seguramente en su sistema, en su macroordenador, superordenador DOJO, ¿no? Que ya nos adelantaron el año pasado este concepto de ordenador modular que están diseñando para el entrenamiento de los coches. Recordemos que al final el problema de la conducción autónoma es un problema que, bueno, de la conducción autónoma completa, el full self-driving, es un problema que todavía no está del todo resuelto y que requiere de una enorme potencia, y por eso Tesla pues está invirtiendo en estos enormes supercomputadores. También seguramente veamos algo de novedades respecto al hardware del coche. Ya sabemos que si el entrenamiento se produce en estos supercomputadores donde generas el modelo, luego ese modelo se tiene que utilizar, se tiene que ejecutar en tiempo real, más rápido incluso que el tiempo real. Tiene que ser procesar información muy rápido a través de todos los sensores que tiene el coche, todas las cámaras, todos los diferentes sensores. Y con esto tiene que tomar decisiones muy rápido, ¿no? Y seguramente nos estén hablando también un poco de cómo funciona todo este hardware. A lo mejor vemos incluso una actualización del sistema de conducción del vehículo. Y por último, lo más emocionante, lo que todo el mundo estamos esperando, después de lo del año pasado, que fue una cosa esperpéntica, son las novedades respecto al Tesla Bot, ¿vale? El Tesla Bot, vamos a irnos vamos a irnos para acá, un momentito. Os voy a compartir este tweet para que, si me lo movéis, gente del chat, os lo agradecería. Así lo vemos en tiempo real. Hace unos días, creo que fue ayer de hecho, Tesla nos enseñó el siguiente GIF, ¿vale? El siguiente GIF. Y este GIF de aquí, lo que nos está mostrando son las manos de lo que será el Tesla Bot, ¿vale? Al parecer han confirmado que esto es un vídeo real de lo que serán las manos del prototipo del Tesla Bot que nos van a enseñar este año. El Tesla Bot, que ya se ha bautizado como Optimus, ese parece ser que va a ser su nombre, el Optimus, ¿no? Una referencia ahí al Optimus Prime. Pues es el concepto de robot humanoide que nos va a presentar Tesla, un poco en competición con la otra gran empresa de robótica humanoide, que sería Boston Dynamics, ¿no? Boston Dynamics sabemos que tiene unos robots espectaculares. Tiene a Atlas como el concepto de robot humanoide. Y es interesante porque aquí la entrada de Tesla a este mercado, permite que este mercado se acelere, que crezca, que se invierta en él. Eso siempre es positivo. Y luego también lo interesante aquí es que el Tesla Bot, de existir, yo le voy a llamar Tesla Bot hasta que me entre lo de Optimus, el Tesla Bot de existir podría adelantar a lo que Boston Dynamics tiene en cuanto a fusión de hardware de la parte de robótica con la parte de inteligencia artificial que ya tiene tan desarrollado el equipo de Tesla, ¿no? Tesla tiene pues el sistema Autopilot para sus vehículos, que al final también no deja de ser un robot, un vehículo, lo que no sería un robot humanoide, pero será la primera empresa que empieza a apostar por esta fusión, porque tenemos un vídeo aquí en el canal, lo sabéis que hay un vídeo sobre cómo funcionan los robots de Boston Dynamics, y en ese vídeo realmente pues os explicaba que todavía no tienen esta inteligencia artificial, este deep learning, este aprendizaje automático tan desarrollado como podría ser lo que nos podría mostrar hoy el señor Elon Musk. Este vídeo, por cierto, os lo recomiendo. Es un vídeo del año pasado, está por aquí, ¿vale? Este vídeo de Atlas está bastante chulo. Entonces lo que vamos a ver hoy es un evento que es espectacular. Y para introducirlo, os voy a enseñar la introducción del vídeo que hice el año pasado respecto al evento del Tesla AI Day, para que veáis un poco de qué va la cosa, ¿vale? Vamos a ponerlo aquí al principio y me confirmáis si se escucha y si se ve bien. Tesla es a día de hoy una de las mayores empresas de robótica del mundo. Sí, como escucháis, de robótica. Y no tiene nada que ver con esto. No, pensadlo bien. El principal producto de una compañía como Tesla son los automóviles. Coches eléctricos que compiten en una industria donde Tesla ha querido diferenciarse buscando resolver la titánica tarea de que estos puedan conducirse solos. Coches autónomos. Todo esto de la mano de los avances que el campo de la inteligencia artificial nos ha ido regalando durante la última década. Y esta es la cosa, el vehículo observa el mundo que le rodea, lo analiza, y en fracción de segundos tiene que tomar la decisión, planificar qué acciones tiene que tomar sobre la mecánica del vehículo para poder desenvolverse en él. Son robots. Elon Musk, CEO de la compañía, sabe que siendo ellos una de las principales empresas de robótica del mundo, intentando resolver estos grandes problemas de la ingeniería, pues está en su deber intentar reclutar a los mejores ingenieros. Y de ahí el motivo de conferencias como la ocurrida la semana pasada, el Tesla AI Day. Una conferencia diseñada por y para ingenieros, catalogadas por muchos, entre los que yo me incluyo, como una de las mejores conferencias técnicas que ha realizado nunca una compañía, al desgranar con todo lujo de detalles todo el trabajo de ingeniería que Tesla ha ido logrando en los últimos años. Y bueno, sí, también ocurrió esto. Y claro, pues habiendo tenido esto, mucha gente y gran parte de la prensa se ha quedado únicamente con el maldito robot, obviando que realmente lo importante es todo lo que nos habían contado previamente. Dicen que cuando el dedo apunta al cielo, el tonto mira al dedo. Así que ya os aviso, sobre el robot hablaré al final, pero ahora nos vamos a centrar en mirar al cielo. Y te voy a explicar todos los detalles que Tesla nos regaló en esta presentación. Poneos los cinturones, porque comenzamos. Por cierto, este vídeo está patrocinado por la nueva edición del Máster Ejecutivo en Inteligencia Artificial que organiza el IIA. Bueno, mira, me viene de perlas. recordaros, aprovecho que está aquí el anuncio, que justamente en este momento del año también está celebrándose, está abierta las plazas para la 5ª edición del Máster Ejecutivo en Inteligencia Artificial del IIA, y que también podéis tener un descuento de 300 euros sobre el precio de la matrícula, y está toda la información abajo en la descripción. El evento del Tesla AI Day, como veis, es un evento pensado, y lo ha dicho el propio Elon Musk, para ingenieros. Para ingenieros. De hecho, vamos a ver mucho contenido que hay que ir desglosando, por eso creo que es interesante que lo veáis a través del canal. Esto va a empezar, por cierto, en 3-4 minutos, o sea que ya vamos a ir yéndonos al canal de Tesla. Pero como digo, esto es un evento pensado para ingenieros. El objetivo principal es que salgan tanto Elon Musk como los profesionales que trabajan con él, cada uno expertos en su ámbito, y nos cuenten de forma súper detallada, o sea, es una auténtica masterclass, conceptos de hardware, robótica, inteligencia artificial, y para gente que le mole la tecnología, que le guste todo lo que vemos en el canal, vais a flipar bastante, ¿vale? Porque suele ser bastante emocionante. Sospecho que este año van a estar muy enfocados en la parte de robótica y en la parte de Optimus. Creo que van a enseñar más de lo que estamos pensando, por una cuestión de que al final este evento lo que pretende es hacer recruitment, que la gente quiera trabajar con ellos, que sea como una ventana para que los ingenieros de todo el mundo digan, oye, esta gente está haciendo cosas chulas, vamos a trabajar. Y ahora necesitan a mucha gente del ámbito de la robótica y de la inteligencia artificial. Entonces, bueno, pues mola bastante. Mientras oiga música en el directo, yo voy a ir muteándolo, porque YouTube se pone bastante tonto con el tema del copyright. Entonces, vamos a dejar esto aquí de fondo de momento, y en cuestión de muy poquito tiempo va a empezar. Y bueno, somos 1000 personas aquí conectados, lo cual me genera pues una tremenda alegría. ¿Vosotros qué tal por el chat? Madre mía, se me meten los bots. Voy a eliminar bots. A ver, un momentito. Hide user. Vale. ¿Vosotros qué esperáis del evento? ¿Cómo lo veis? Del 1 al 10, ¿qué expectativas tenéis sobre el Tesla Bot? ¿Qué pensáis? ¿Va a ser un 1? Es decir, ¿va a salir de nuevo un señor bailando vestido en pijamas? ¿Va a ser, por ejemplo, un 5? Vamos a ver un prototipo, pero que es bastante convencional, que no se acerca, por ejemplo, a lo que tiene Boston Dynamics, que no se acerca, por ejemplo, a lo que tiene la gente de Ameca, creo que se llaman, ¿no? Si no me equivoco. Vamos a ver si lo puedo abrir rápido por aquí. Ameca, creo que es el robot. Vale, este es el robot Ameca de la gente de Engineer Arts, que es un robot espectacular. O vamos a ver un 10. A lo mejor nos sorprenden de verdad. Yo consideraría que estaríamos viendo un prototipo muy interesante si vemos un robot humanoide caminando, completamente independiente, es decir, sin ningún tipo de sujeción, ¿sabes? Que no esté conectado, por ejemplo, a un cable en el techo para evitar que se caiga. Yo quiero que tengan la confianza. Vale, ya estamos empezando, creo. Que tengan la confianza para dejarlo suelto y verlo andar y articular y coger cosas. Vale, no, solo han cambiado la animación del Windows Player. Un 8. Bueno. Veo gente, un 6, un 2pi, un 4,20, un 9. ¡Guau! ¡Qué rico! Me vais a escuchar también ir comiendo en directo, oye. Pues lo que os comentaba antes, aprovechando, voy a meter aquí el tema del máster, ya que también lo hicimos el año pasado. El máster del Instituto de Inteligencia Artificial es un máster que empieza el 15 de octubre y es online. Y esto ya está empezando, así que si queréis más información lo ponéis abajo. 3, 2, 1. Y esto... ¡Yes! Ojo, Vámonos. Es el malo de una peli. Bueno, han empezado puntual, que eso ya es un logro.
All right, welcome everybody. Let's give everyone a moment to
Hostia.
get back in the audience.
Ese momento de colocar a la audiencia ahí.
All right, great. Welcome to Tesla AI Day 2022.
Vámonos. Voy a poner los subtítulos generados por IA, a ver qué tal sale.
We've got some really exciting things to show you. I think you'll be pretty impressed. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot suit. But we've come a long way, and it's I think compared to that, it's going to be very impressive.
Que vamos a ver cosas del robot Optimus, que a partir de lo que era un señor disfrazado de robot, pues ha mejorado bastante.
More generally to real-world AI problems like a humanoid robot and even going beyond that. I think there's some potential that what we're doing here at Tesla could make a meaningful contribution to AGI.
Ojo,
And I think actually Tesla
están hablando de inteligencia artificial general.
From a governance standpoint, because we're a publicly traded company with one class of stock, and that means that the public controls Tesla, and I think that's actually a good thing. So if I go crazy, you can fire me. This is important. Maybe I've gone crazy. I don't know.
No hay en español, los subtítulos.
So,
os iré contando.
Yeah, so we're going to talk a lot about our progress in AI, Autopilot, as well as progress with DOJO. And then we're going to bring the team out and do a long Q&A, so you can ask tough questions.
Lo dicho, van a hablar de Autopilot, de DOJO,
existential questions, technical questions.
De Optimus.
We want to have as much time for Q&A as possible. So,
no se pueden cambiar los subtítulos a español, ¿eh?
Because what? Say anything?
Hey guys, I'm Milan. I work on Autopilot and the Tesla Bot.
And I'm Lizzie, mechanical engineer on the project as well.
Okay.
Vale.
So should we bring out the bot?
Before we do that,
El robot.
we
El robot. Van a traer el robot.
one little bonus tip for the day. This is actually the first time we try this robot without any backup support, cranes.
Ahí está, justo. Es la primera vez que lo van a probar sin ningún tipo de grúa, sin sujeciones, sin nada. Se puede ir al piso, al suelo, y va a ser espectacular. Van a sacar el robot ya. Ese es el nivel. Ojo, Vámonos. Hostia, qué miedo, tú. Ok. Hostia. A ver. Hostia, da miedo, Y está guapo. Camina. Ay Dios. Ay Dios. Estoy sufriendo, Ojo, han avanzado. Está guapo, O sea...
I think the bot got some moves too.
Se mantiene. Vale. Hostia, da todo el miedo,
So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
Acaba de decir que tiene el mismo ordenador que tienen los Tesla Cars, los vehículos de Tesla.
This is literally the first time the robot has operated without a tether. Was on stage tonight.
La primera vez que camina en el escenario sin ningún tipo de sujeción, lo que decíamos al principio, ¿no? Hostia, está guapo, Además la versión del robot así sin carcasa, sin nada. Luces y cables. Hostia, da miedo, Da yuyu. Da yuyu. El movimiento todavía es muy articulado, no tiene para nada la movilidad que tienen los robots de Atlas. Creo que el tema de los actuadores aquí estaban intentando tener actuadores eléctricos. Que puede hacer más cosas, pero que no han querido que se caiga de cara, así que bueno. Luego nos lo van a enseñar.
yeah, which are less risky. Yeah.
We should close the screen, guys.
Mira, 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 mira.
Yeah.
Ahí está. Dios, qué guapo. Mira la vista del robot.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot and just walking around and dancing on.
¿Ves? Ahí está. Ahí sí está sujeto.
Just humble beginnings, but you can see the Autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my
No está
work.
mal, ¿eh?
Yeah, when
No
you,
está
when you see a
mal.
rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up.
Esto es la vista del robot, ¿vale? Y vemos cómo hace una segmentación en tiempo real, diferenciando diferentes
We
objetos
use
y
the
todo.
same process as we did for Autopilot to collect
Y eso está
data and
guapo,
train
porque esto sí que
neural
Atlas no lo
networks that
usa.
we then deploy on the robot. That's an example that illustrates the upper body a little bit more.
And
Something
this
that
is
we'll
really-
like try to nail down in a few months, over the next few months, I would say, to perfection.
This is really an actual station in the Fremont factory as well that it's working at.
Yo te digo, me encierras en una fábrica con 10 de estos y me acojono. O sea, me acojono. Yo... a mí que me dejen
That's not the
teletrabajando.
only thing we have to show today, right?
Yeah, absolutely. So.
Bueno, lo primero que nos han enseñado, ¿qué os ha parecido? Del 1 al 10.
Sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's
Está
done an
bastante
incredible
bien,
job. And we actually have an Optimus Bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things.
Vale. Ha gustado, ha gustado.
Do it.
Vale, y este no camina, pero es como esperan que se vea el robot cuando esté bien. Ojo, que se va, que se queda para adelante. Este no camina. Este ya tiene esclavizado a los humanos. Vemos que la parte de arriba sí está articulado. Madre mía. Vale, este se mueve la parte de arriba. Pero así es como alucinan los robots. Bastante guapo. Pues esto es Optimus,
So here
amigos.
you're using Optimus with these are with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs.
Todos los dedos se mueven
and, both left and
independientemente,
right
los
hand,
pulgares
so it's
también.
able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. And we've also designed it using the same discipline that we use in designing the car, which is to design it for manufacturing such that it's possible to make the robot in high volume at low cost with high reliability. So that's incredibly important. I mean, you've all seen very impressive humanoid robot demonstrations, and that's great, but what are they missing? They're missing a brain.
Vale.
They don't have the
Aquí están haciendo referencia a los robots
the
de
world
Boston
by
Dynamics, sí, es
themselves.
justo lo que comentábamos
And
antes, ¿no?
They're also very expensive and made in low volume.
Son robots muy
Whereas,
caros,
the Optimus
que no se
is
pueden
like
diseñar en
an
serie
extremely powerful
y que no
robot,
tienen cerebros, no tienen
made in
inteligencia
very high
artificial.
volume, probably ultimately millions of units, and it is expected to cost much less than a car.
I'll just bring it
So,
directly to the right here.
I would say probably less than $20,000.
Menos de $20.000.
Would be my guess.
Sí, bueno, las cifras de Elon siempre nos las tomamos como como un chiste, pero ojo,
The potential for Optimus is, I think, appreciated by very few people.
Hey!
Hasta luego.
As usual, Tesla demos are coming in hot. So,
Okay, that's good. That's good.
yeah.
Los de Boston no usan IAM, por eso.
The team has put in an incredible amount of work, working days, 7 days a week.
Ojo que para hacer un año de trabajo está bastante bien, ¿eh? Evidentemente el año pasado no empezaron a trabajar desde el día del AI Day, ¿no? Pero ya tendrían cosas desarrolladas, pero tienen algo bastante sólido para seguir trabajando.
So, now there's still a lot of work to be done to refine Optimus and improve it. Obviously, this is just Optimus version 1. And that's really why we're holding this event, which is to convince some of the most talented people in the world, like you guys, to join Tesla and help make it a reality and bring it to fruition at scale such that it can help millions of people.
Aquí está hablando un poco de una invitación a los ingenieros a trabajar en Tesla, que es el objetivo principal de este evento, ¿no?
Sort of productive entities times their productivity, capita times output, productivity per capita. At the point at which there is not a limitation on capita, it's not clear what an economy even means at that point. An economy becomes quasi-infinite. So, what taken to fruition in the hopefully benign scenario, this means a future of abundance, a future where there is no poverty, where you can have whatever you want in terms of products and services. It really is a fundamental transformation of civilization as we know it. Obviously, we want to make sure that transformation is a positive one and safe. But that's also why I think Tesla as an entity doing this, being a single class of stock publicly traded, owned by the public, is very important and should not be overlooked. I think this is essential because then if the public doesn't like what Tesla's doing, the public can buy shares in Tesla and vote differently. This is a big deal. It's very important that I can't just do what I want. Sometimes people think that, but it's not true.
Está divagando muchísimo.
It's very important that the corporate entity that makes this happen is something that the public can properly influence. So I think the Tesla structure is ideal for that. And like I said, that self-driving cars will certainly have a tremendous impact on the world. I think they will improve the productivity of transport by at least a half order of magnitude, perhaps an order of magnitude, perhaps more. Optimus, I think, has maybe a 2 order of magnitude potential improvement in economic output.
A ver.
It's not clear what the limit actually even is.
Está comentando, ¿no? Como los productos que están sacando, la conducción autónoma y el Optimus, pues van a hacer que la economía se pueda desarrollar, pueda crecer. El crecimiento de una economía puede ser infinita y podemos vivir en un futuro de abundancia, sin pobreza, y que esto para la humanidad es la hostia. Y que por eso tenéis que trabajar en Tesla. Y es interesante, ¿no? Ha dicho, los coches de Tesla, la conducción autónoma, puede tener un futuro. Voy a intentar no solaparme mucho con Elon, pero lo digo.
So we want to do the right thing. So consider joining us and helping make it happen. With that, let's move on to the next page.
Right on. Thank you, Elon.
Muy bien, Elon. Ha dicho una cosa interesante, que es que los coches de Tesla pues pueden tener un impacto en la economía de medio orden de magnitud. Y los Optimus, calcula él, una estimación un poco al vuelo, de 2 órdenes de magnitud. Entiendo que 2 cifras o no sé si un por 2, pero bueno. O sea que para ellos ven más futuro en la parte del robot que la parte de los coches.
Working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. So this guy is rooted in the foundation of sort of the vehicle design process. You know, we're leveraging all of those learnings that we already have. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form.
Pesa poco, ¿eh? Ah, no, coño, esto es un humano,
But
joder.
it's fun. We spend a lot of time thinking about how amazing the human
Perdón,
body
es
is.
tarde.
We have this incredible range of motion, typically really amazing strength. A fun exercise is if you put your fingertip on the chair in front of you, you'll notice that there's a huge range of motion that you have in your shoulder and your elbow, for example. Without moving your fingertip, you can move those joints all over the place. But the robot, you know, its main function is to do...
Comentando cómo se inspiran, ¿no? en la forma y la biología humana y lo compleja que es. La cantidad de joints que tenemos, de articulaciones que tenemos en el cuerpo es impresionante.
Humans are also pretty efficient at some things and not so efficient in other times. So for example, we can eat a small amount of food to sustain ourselves for several hours. That's great. But when we're just kind of sitting around, no offense, but we're kind of inefficient. We're just sort of burning energy. So on the robot platform, what we're going to do is we're going to minimize that idle power consumption, drop it as low as possible. And that way we can just flip a switch and immediately the robot turns into something that does useful work. So let's talk about this latest generation in some detail, shall we? So on the screen here you'll see in orange our actuators.
Los actuadores que van a ser las articulaciones del robot.
So now that we have our sort of human-based research, and we have our first development platform, we have both research and execution to draw from for this design. Again, we're using that vehicle design foundation, so we're taking it from concept through design and analysis, and then build and validation. Along the way, we're going to optimize for things like cost and efficiency, because those are critical metrics to take this product to scale eventually. How are we going to do that? Well, we're going to reduce our part count and our power consumption of every element possible. We're going to do things like reduce the sensing and the wiring at our
Quieren reducir
extremities.
todo el
Imagine
consumo
a lot of
eléctrico del
mass in
robot
your hands
en la medida de lo posible, ¿no? Quieren
quite
optimizar
difficult and power
ese
consumptive
parámetro
to
porque
move around.
consideran que es fundamental para la
And we're
autonomía del
gonna
robot,
centralize
evidentemente
both our
tiene todo
power
el sentido.
distribution and our compute to the physical center of the platform. So in the middle of our torso, actually it is the torso, we have our battery pack.
¿Vale? Aquí está el
This is
battery
sized
pack.
at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So that means everything from sensing to fusing, charge management, and power distribution is all in one place. We're also leveraging both our vehicle products and our energy products to roll all of those key features into this battery. So that's streamlined manufacturing, really efficient and simple cooling methods, battery management, and also safety. And of course, we can leverage Tesla's existing infrastructure and supply chain to make it.
Aquí hay una diferencia con respecto a Boston Dynamics y son los actuadores. Si no recuerdo mal, todo el sistema de Atlas es hidráulico. Es hidráulico, ¿vale? Y aquí esto es eléctrico. Y recuerdo que el hidráulico tiene mejor resistencia y articulación para moverse, pero se rompen más. Hostia, no es súper loco que estemos viendo esto. Esto es puto ciencia ficción, ¿eh?
Processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well. But before we do that, I'd like to introduce Malcolm, who's going to speak a little bit about our structural foundation for the robot.
Thank you, Lizzie. Tesla have the capabilities to analyze highly complex systems. They don't get much more complex than a crash. You can see here a simulated crash from Model 3 superimposed on top of the actual physical crash.
Qué guapo.
It's actually incredible how accurate it is. Just to give you an idea of the complexity of this model, it includes every nut, bolt, and washer, every spot weld, and it has 35 million degrees of freedom. It's quite amazing. And it's true to say that if we didn't have models like this, we wouldn't be able to make the safest cars in the world. So can we utilize our capabilities and our methods from the automotive side to influence a robot?
Vale, dicen que bueno, que Tesla tiene la capacidad de hacer modelos espectaculares, como el modelo que hemos visto ahí de choque, y cómo pueden utilizar eso, aprendido de la automoción, para hacer un buen robot. Control de daño, ¿vale? Estamos viendo cómo pueden estimar los daños que se hace el robot en todas las caídas y todos los golpes que se darán en la fase de experimentación.
We can also take the same model and we can drive the actuators using the inputs from a previously solved model, bringing it to life. So this is producing the motions for the tasks we want the robot to do. These tasks are picking up boxes, turning, squatting, walking upstairs. Whatever the set of tasks are, we can play to the model. This is showing just simple walking. We can create the stresses in all the components that helps us to optimize the components. These are not dancing robots. These are actually the modal behavior, the first 5 modes of the robot. And typically, when people make robots, they make sure the first mode is up around the top single figures, up towards 10 hertz. The reason to do this is to make the controls of walking easier. It's very difficult to walk if you can't guarantee where your foot is wobbling around. That's okay if you make one robot. We want to make thousands, maybe millions. We haven't got the luxury of making them from carbon fiber and titanium. We want to make them from plastic. Things are not quite so stiff. So we can't have these high targets. I call them dumb targets. We've got to make them work at lower targets. So is that going to work? Well, if you think about it, sorry about this, but we're just bags of soggy jelly and bones thrown in. We're not high frequency. If I stand on my leg, I don't vibrate at 10 hertz. People operate at low frequency, so we know the robot actually can. It just makes controls harder. So we take the information from this, the modal data and the stiffness, and feed that into the control system. That allows it to walk. Just changing tack slightly, looking at the knee. We can take some inspiration from biology.
La comparación entre la rodilla humana y la rodilla del robot.
Represent quite similar to 4-bar link, and that's quite non-linear. That's not surprising, really, because if you think when you bend your leg down, the torque on your knee is much more when it's bent than it is when it's straight. So you'd expect a non-linear function. And in fact, the biology is non-linear. This matches it quite accurately. So that's a representation. The 4-bar link is obviously not physically a 4-bar link. As I said, the characteristics are similar. But me bending down, that's not very scientific. Let's be a bit more scientific. We've played all the tasks.
Ojo, con grafiquitas y todo. Es que esto es serious business. Está hablando como el tema de doblar la rodilla. No es un proceso lineal donde siempre estás haciendo como una apertura a la misma velocidad, sino que varía en el tiempo, ¿no? Y que tienen que imitar eso para conseguir un buen control. Tienen que imitar a la naturaleza en ese sentido.
So if we look at the 4-bar link, that's actually the green curve. And it's saying that the non-linearity of the 4-bar link has actually linearized the characteristic of the force. What that really says is that's lowered the force. That's what makes the actuator have the lowest possible force, which is the most efficient. We want to burn energy up slowly. What's the blue curve? Well, the blue curve is actually if we didn't have a 4-bar link, we just had an arm sticking out of my leg here with an actuator on it, a simple 2-bar link. That's the best we could do with a simple 2-bar link, and it shows that that would create much more force in the actuator, which would not be efficient. So what does that look like in practice? Well, as you'll see, it's very tightly packaged in the knee. You'll see it go transparent.
Esto es como se vería la rodilla si usaran un solo actuador para la rodilla.
and the displacements on the actuator. I'll now pass you over to Konstantinos, who'll tell you a lot more detail about how these actuators are made and designed and optimized. Thank you.
O sea, entiendo esto es cómo se vería. Bueno, no he terminado de entender si era la versión correcta o la que quieren mejorar.
So, I would like to talk to you about the design process and the actuator portfolio in our robot. So there are many similarities between a car and the robot when it comes to powertrain design. The most important thing that matters here
la transferencia de conocimiento que están haciendo de un sector a otro, ¿no? De los vehículos, del automóvil, a construir un robot, que es algo que nunca se ha hecho antes. Bueno, Honda tenía comprada la empresa esta de robótica, del robotito pequeño, pero bueno.
And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive side. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process. This is one of the scenarios that the robot is capable of doing, which is turning and walking. So when we have this torque speed trajectory, we lay it over an efficiency map of an actuator, and we are able, along the trajectory, to generate the power consumption and the energy, cumulative energy for the task versus time. So this allows us to define the system cost for the particular actuator and put a simple point into the cloud. Then we do this for hundreds of thousands of actuators by solving in our cluster. And the red line denotes the Pareto front, which is the preferred area where we will look for our optimal. So the X denotes the preferred actuator design we have picked for this particular joint. So now we need to do this for every joint. We have 28 joints to optimize, and we parse our cloud. We parse our cloud, again, for every joint spec, and the red axis this time denote the bespoke actuator designs for every joint. The problem here is that we have too many unique actuator designs, and even if we take advantage of the symmetry, still there are too many. In order to make something mass manufacturable,
estoy callado porque o escucho o hablo, pero no puedo hacer las dos cosas a la vez.
Therefore, we run something called Commonality Study, which we parse our cloud
podría ir pausando si queréis y vamos comentando cosas, pero joder.
Meet the joint performance requirements for more than one joint at the same time. So the resulting portfolio is 6 actuators, and they show in a color map at the middle figure. And the actuators can be also viewed in this slide. We have 3 rotary and 3 linear actuators, all of which have a great output force or torque per mass. The rotary actuator in particular has a mechanical clutch integrated. On the high-speed side, angular contact ball bearing.
Estos actuadores los han diseñado ellos, que recuerdo que hace un año estaban buscando expertos, se veía como la posición de trabajo, la oferta de empleo, de que estaban buscando mecánicos para hacer los siguientes actuadores que se utilizarían en la industria, ¿no?
The linear actuator The linear actuator has planetary rollers and an inverted planetary screw as a gear train, which allows efficiency and compaction and durability. So in order to demonstrate the force capability of our linear actuators, we have set up an experiment in order to test it under its limits. And I will let you enjoy the video. So our actuator is able to lift.
¿Qué está levantando? ¿Un coche? Nah. Ojo, a ver.
A half-ton, 9-foot
Toma ya, ¿eh?
concert grand piano. And
Qué guapo.
this is a requirement. It's not something nice to have, because our muscles can do the same when they are direct driven. When they are directly driven, our quadricep muscles can do the same thing. It's just that the knee is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague Mike, who is going to talk to you about hand design. Thank you very much.
Vale, ahora van a hablar de la mano, ¿no? Nos han hablado un poco de los actuadores, que serían los músculos del robot.
So we just saw how powerful a human and a humanoid
Vamos a ver la mano. La mano,
actuator
el robótica, eso era
However,
un
humans are
proyecto
also
que OpenAI
incredibly
tenía
dexterous.
y que desapareció. Porque se cargaron todo el
Human hand
sistema
has
de
the ability
robótica
to move
de
at 300
de
degrees per
OpenAI.
second.
Y muchos de los
There's
ingenieros se
10,000
sospecha que pueden haber
tactile
acabado en
sensors.
Tesla.
It has the ability to grasp and manipulate almost every object in our daily lives. For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hand as well. The converse there is pretty interesting because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object.
Un poco la lógica de lo de la mano es lo mismo que la de la propia existencia del robot humanoide, ¿no? ¿Por qué crean un robot humanoide? ¿Por qué crean una mano humana? Porque quieren aprovechar la ergonomía del mundo que está diseñado para nosotros. Entonces, si haces una mano humana, pues puedes utilizar las herramientas que usamos los humanos. Un poco raro, pero... Ok.
One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors. You just heard how we went about designing the Tesla Bot hardware. Now I'll hand it off to Milan and our autonomy team.
Madre mía, los bots del chat, ¿eh? Qué horror.
All right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months, thanks to the amazing work that we've done on Autopilot over the past few years. Most of those components ported quite easily over to the
Vale, ya está, ya
bot
hemos pasado de la mano.
If you think about it, we're just moving
Y ahora la
from
parte del
robot on
software, ¿no?
wheel
La parte de
to
inteligencia
robot on
artificial.
legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from Autopilot to the bot's situation.
Ahí está,
It's
¿no?
exactly the same occupancy network that we'll talk into a little bit more details later with the Autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect.
Tiene 3 cámaras, ¿no? Por lo que parece.
We're also trying to find ways to improve those occupancy networks
Vale, esto es usando NERF.
using work made on neural radiance fields
Ahí está.
to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to
Están usando NERF
interact
para poder darle más
Another interesting
posibilidades al
problem
robot
to
de
think
entender
about
el
is,
entorno, ¿no? Que la
in
rodea.
indoor environments,
Tiene
mostly,
cámara derecha, izquierda y
with
ojo de
absence
pez.
of GPS signal. How do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training
Qué guapo,
more neural networks to identify
Me está flipando, que están haciendo un robot, me está flipando.
within the bot's camera streams.
No daba un
and
duro
track
por
them
ello, ¿eh?
across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. We also did quite some work on the simulation side. And this is literally the Autopilot simulator, to which we've integrated the robot's locomotion code.
Vale, aquí nos están hablando también del simulador que han creado para poder simular la mayoría de cosas que necesitan, ¿no? Y es como el simulador que usaban para Autopilot, ahora para el robot.
So as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over
Tío, están haciendo robots, es que no...
So locomotion is specifically one component.
Está muy verde, sí, está muy verde, pero
as we're moving from the car to the bot
se está moviendo muy rápido, que eso es lo
So I think
importante.
it warrants a little bit more depth, and I'd like my colleagues to start talking about this now.
Thank you, Milan. Hi, everyone. I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking which are challenging from an engineering perspective. For example, physical
Mira cómo camina,
self-awareness.
mira cómo camina
That
esta
means
persona.
having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy-efficient gait. You can imagine there's different styles of walking, and all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally.
Yo no camino, soy youtuber,
But
amigo.
as engineers or roboticists, we have to think about these problems. And in the following, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bot, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages.
Vale, esto sí es parecido a cómo funcionaba Atlas, ¿no? Tú tienes un modelo del robot, o sea, el robot, el cerebro del robot se hace como un modelo del mundo por donde camina, tiene una ruta que quiere cumplir, que es la línea blanca que vemos aquí, y va planificando, va adaptándose a los posibles obstáculos, a lo que pueda haber, va planificando cuál es su trayectoria, ¿no? Para que luego los actuadores se muevan y cumplan esa instrucción.
The last stage is then finding a center of mass trajectory, which gives us a dynamically feasible motion of the entire system to keep balance. As we all know, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Se van cambiando todo el rato.
Thank you, Felix. Hello, everyone. My name is Anand, and I'm going to talk to you about controls. So let's take the motion plan that Felix just talked about and put it in the real world on a real robot. Let's see what happens.
Se va a caer al suelo. Se va a caer al suelo.
It takes a couple steps and falls down.
Es que lo
Well, that's
sabía.
a little
Hostia, sabe volar tú.
But we are missing a few key pieces here, which will make it walk. Now,
Vale.
as Felix mentioned, the motion planner is using an idealized version of itself.
Como hemos visto, ¿no? En el paso anterior se planifica lo que el robot debería de hacer y cuando lo ejecutas en el mundo real, cuando pasas de la simulación al mundo real, falla. Porque faltan cosas todavía.
Through trajectories and wrenches. Wrenches are forces and torques that it wants to exert on the world to locomote. Reality is way more complex than any sim or model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled
El mundo real es
dynamics,
mucho más
which
complejo
essentially the
que
plan
las
doesn't know
simuladores
about.
que podemos
And that
crear ahora
causes
mismo, entonces esas dinámicas que no tenemos
especially
modeladas,
for a
pues,
system
por
that is
decir una,
dynamically
el
stable
viento, por
like pipeline
ejemplo,
locomotion.
pues hace que el robot se vaya
What
al
can we do
suelo.
about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And state estimation, here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human,
Ahí está.
along with the center of mass
Te
trajectory.
utilizan un montón de sensores
when the robot's walking in the office
y
environment.
para medir el estado del robot y
Now we have all
a la
the
altura de la
pieces we
pelvis
need
pues hacen
in order
como
to
esta
close the
situación de
loop.
equilibrio, ¿no? Van reajustando
use
para que
our
el robot
better bot
pues no se
model.
caiga.
we use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect the reality.
Venga, también le están
expect the
pegando
reality is
como
doing to us
Boston Dynamics.
in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright.
Así empieza la revolución de las máquinas. Esto lo recordarán.
A robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
Vale. ¿Cómo utiliza las manos y las piernas? No, bueno, las piernas para manipular no, pero las manos sí. Está muy por detrás de los de Boston Dynamics, evidentemente, pero es que Boston Dynamics llevan 20 años. Mirad los primeros prototipos de Boston Dynamics y comparad con esto. Poco a poco, paso a paso. Vale, destreza para manipular objetos, ¿no? Con la mano, entiendo.
First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here.
Quieren crear como una librería de acciones de referencia como punto de partida para el robot. Y están utilizando motion capture.
But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular
Pero claro, el movimiento que ha hecho el humano es solo una referencia de coger una caja, pero las cajas pueden estar en miles de lugares al mismo tiempo, entonces tenemos que entrenarlo para generalizar esa tarea.
So for instance, if the box is in this location, then our optimizer
Ahí está, ¿ves cómo se optimiza para coger el objeto?
Next, Milan's going to talk about what's next for the Optimus Tesla bot.
Este no quería hablar mucho. Este se ha pirado. A la pa' casa.
Right, so hopefully by now you guys got a good idea of what we've been up to over the past few months.
Esto es lo que han trabajado los últimos meses y ahora vamos a ver cuál es el futuro, ¿no? de lo que está por venir.
I think the first thing within the next few weeks is to get Optimus at least at par with Bumblebee, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories and really going to try to nail this down and iron out all the elements needed to deploy this product in the real world. I was mentioning earlier, indoor navigation, graceful floor management, or even servicing, all components needed to scale this product up. But I don't know about you, but after seeing what we've shown tonight, I'm pretty sure we can get this done within the next few months or years and make this product a reality and change the entire economy. So I would like to thank the entire Optimus team for all their hard work over the past few months. I think it's pretty amazing. All of this was done in barely 6 or 8 months. Thank you very much.
Todo esto que hemos visto dicen que se ha hecho en 6 meses. Y qué bueno que realmente confían en que van a seguir trabajando en esto y que se van a convertir en una empresa de robótica y que van a transformar la economía del mundo. Y oye, me lo creo más que el año pasado, porque el año pasado no teníamos nada. Parecía como un golpe de efecto, ¿no? Para subir la marca de Tesla, pero joder. Ojo.
Anyway, every Tesla that has been built over the last several years, we think has the hardware to make the car drive itself. We have been working on the software.
Roy, te recomiendo que veas el vídeo que tengo sobre Atlas en el canal. Ahí lo comento, cómo funciona Atlas. Vale. Autopilot.
We have significantly improved the software's robustness and capability that we have now shipped it to 160,000 customers as of today.
Autopilot, recordemos, el software que hace que los coches de Tesla se puedan conducir solos y que el objetivo es que tengan conducción completa. Completa, ojo. Que un humano no tenga que usar el volante.
Neural network models just last 1 year. That's roughly a model every 8 minutes. that's coming out of the team, and then we evaluate them on our large clusters, and then we ship 281 of those models that actually improve the performance of the car. And this pace of innovation is happening throughout the stack. The planning software, the infrastructure, the tools, even hiring, everything is progressing to the next level. The FSD beta software is quite capable of driving the car. It should be able to navigate from
Han entrenado 75.000 modelos, chavales.
Stopping for traffic lights and stop signs, negotiating with objects at intersections, making turns, and so on. All of this comes from the camera streams that go through our neural networks that run on the car itself. It's not coming back to the server or anything. It runs on the car and produces all the outputs to form the world model around the car, and the planning software drives the car based on that.
Nos están contando un poco
components that make up the system.
Las cifras actuales del proyecto de Autopilot.
Acts as the base geometry layer.
Esto es un poco el esquema de cómo funciona.
This is a multi-camera video neural network that from the images predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, balls, what have you, it predicts, if it's physically present, it predicts them, along with their future motion. On top of this base level of geometry, we have more semantic layers. In order to navigate the roadways, we need the lanes, of course.
Es como un esquema a muy alto nivel de cómo funciona el coche, ¿no? Una red que predice la ocupancia, dónde hay obstáculos, dónde hay vacío y dónde hay obstáculos, que es un poco la imagen que hemos visto antes de voxeles, de todo el espacio tridimensional con muchos cubitos, pues eso es lo que predice el occupancy. Y luego por el otro lado la predicción de los carriles y los objetos que puedan haber. Todo esto usando redes neuronales de visión por computador que nos van a contar ahora seguramente.
All of this directly comes from neural networks. Video streams, raw video streams, come into the networks, go through a lot of processing, and then outputs the full kinematic state, like positions, velocities, acceleration, jerk, all of that.
De los objetos no solo se predice el objeto en un fotograma, sino que se predice la dinámica del objeto, ¿no? Un coche, a qué velocidad se mueve, hacia dónde se mueve, todo.
These networks predicts fourth derivatives of these positions, and people thought we couldn't even detect these objects. My opinion is that it did not come for free. It required tons of data, so we had to build sophisticated auto-labeling systems that churn through raw sensor data, run a ton of offline compute on the servers. It can take a few hours, run expensive neural networks.
Vale, esto lo vimos el año pasado, ¿no? Cómo hacen el entrenamiento de estas redes neuronales, pues, por una parte, haciendo sistemas de autoetiquetado, es decir, cogen clips de los coches, vídeos y los etiquetan, pero claro, no manualmente, sino automáticamente. Luego también hacen simulaciones de carretera. Y luego tiene un sistema, ¿vale? El sistema para obtener datos, ¿no? Recopilar datos. Despliegan el modelo en los vehículos, detectan dónde están los fallos concretos y con esto luego recuperan más datos de donde el coche ha podido fallar más. Todo esto el año pasado está súper detallado y eso está en el vídeo que está subido al canal si lo queréis revisar, ¿eh?
Sits us at about 14,000 GPUs today across multiple training clusters in the United States. We also worked on our AI compiler, which now supports new operations needed by those neural networks and map them to the best of our underlying hardware resources. And our inference engine today is capable of distributing the execution of a single neural network across two independent systems on chips, essentially two independent computers interconnected within the same full self-driving computer. And to make this possible, we had to keep a tight control on the end-to-end latency of this new system. So we deployed more advanced.
Curioso, porque todo esto el año pasado lo presentó Andrew Karpathy, que es el investigador líder de Tesla de inteligencia artificial hasta hace unos meses, porque dejó la compañía. Y es una pena, porque era un tío majete y explicaba las cosas súper bien.
Using a combination of model-based optimization plus neural network that helps optimize it to be really fast.
¿vale? Con la detección de dónde están los obstáculos y todos los objetos y carriles, pues lo que falta es que el coche haga la planificación de cómo se va a mover, ¿no?
Not just the car, but the same components also run on the Optimus robot that Milan showed earlier. With that, I welcome Padel to start talking about the planning section.
Parece que este año no se van a meter tanto en cómo funciona el Autopilot, ¿no? Ya eso lo hicieron el año pasado. Tenéis el vídeo para ver exactamente cómo funciona. Está bastante guapo, ¿eh?
Let's use this intersection scenario to dive straight into how we do the planning and decision making.
Nos van a hablar de la parte de planificación, de cómo cuando ya has hecho toda la detección de lo que detectan las cámaras del Autopilot, cómo el coche planifica qué hace. Que todavía el coche genera errores, ¿eh? Hay vídeos en YouTube de coches girando fuerte o saliéndose de carriles.
And also understand the relation between the pedestrian and the vehicle on the other side of the intersection. It's a lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that Autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal lateral profile. Now, obviously, we are being
Opción 1, pasar por delante del peatón y que aprenda que por ahí no se cruza, ¿eh?
We could have moved forward slowly, shot for a gap between the pedestrian and the vehicle from the right.
Ir lento y decirle al coche humano que te joda.
But outright reject this interaction in case this is only safe interaction available.
Atropellar al perro no es una opción.
Lastly, the interaction we ended up choosing. Stay slow initially, find the reasonable gap, and then finish the maneuver after all the agents.
Vale. Esperar, claro. Ser un buen ciudadano.
The evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far. Because you will miss out on a lot
Esas matrices no están bien, hay errores.
This basically boils down to solving a multi-agent joint trajectory planning problem.
Nada, esa fórmula está mal. Faltan índices.
Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem.
Bueno, que tienen que optimizar, para tomar la decisión tienen que resolver un problema de optimización que además se tiene que resolver en milisegundos, ¿no? Porque tú tienes que tomar una decisión en tiempo real. Eso es súper complicado.
Say you have more than 20 objects. Each object having multiple different future modes, the number of relevant interaction combinations will blow up.
Y que claro, a más número de objetos, pues va creciendo exponencialmente el orden de complejidad.
How do we solve this in real time? We rely on a framework what we call as interaction search, which is basically a parallelized tree search over a bunch of maneuver trajectories. The state space here corresponds to the kinematic state of ego, the kinematic state of other agents, their nominal future multimodal predictions, and all the static entities in the scene. The action space is where things get interesting. We use a set of maneuver trajectory candidates to branch over a bunch of interaction decisions and also incremental goals for a longer horizon maneuver. Let's walk through this research very quickly to get a sense of how it works.
Bueno, que plantean como una especie de árbol de diferentes decisiones que donde van a recorrer pues van a recorrer ese árbol para buscar la opción óptima, ¿no?
Lanes again from the lanes network or unstructured regions which correspond to a probability mask derived from human demonstration. Once we have a bunch of these goal candidates, we create seed trajectories using a combination of classical optimization approaches as well as our network planner, again trained on data from the customer fleet. Now, once we get a bunch of these seed trajectories, we use them to start branching on the interactions. We find the most critical interaction. In our case, this would be the interaction with respect to the pedestrian, whether we assert in front of it or yield to it. Obviously, the option on the left is a high penalty option. It likely won't get prioritized. So we branch further onto the option on the right, and that's where we bring in more and more complex interactions, building this optimization problem incrementally with more and more constraints. And the tree search keeps flowing, branching on more interactions, branching on more goals. Now, a lot of tricks here lie in evaluation of each of this node of the tree search.
Acabo de caer que
Inside each node, initially
si
we
hago
started
así,
with
aparece
creating
el señor
trajectories using
para
classical
vosotros.
optimization approaches, where the constraints like I described would be added
Ahora sí, como si
incrementally.
fuera él.
And this would take close to 1 to 5 milliseconds per action.
Me disculpa a los ingenieros
Now, even though this is
ocultos.
a fairly good number, when you want to evaluate more than 100+ interactions, this does not scale. So we ended up building lightweight queryable networks that you can run in the loop of the planner. These networks are trained on human demonstrations from the fleet, as well as offline solvers with relaxed time limits. With this, we were able to bring the runtime down to close to 100 microseconds per action.
Bueno, pues el proceso de optimización de rutas, que la verdad que han explicado aquí una cosa que hay que digerirlo para...
You still have this massive tree search that you need to go through, and you need to efficiently prune the search space. So you need to do scoring on each of these trajectories. Few of these are fairly standard. You do a bunch of collision checks, you do a bunch of comfort analysis, what is the jerk and axle required for a given maneuver. The customer fleet data plays an important role here again.
Sí, sí, doy yo la ponencia.
Again, lightweight queryable networks, both really augmenting each other. One of them trained from interventions from the FST beta fleet, which gives a score on how likely is a given maneuver to result in interventions over the next few seconds. And second, which is
Esto es lo que vimos el año pasado, ¿no? Que consiguen generar como una distribución de trayectorias para cada decisión que quieren tomar y luego pueden como optimizarla, que se veía, por ejemplo, optimizarla para que sea la trayectoria que más confort genere para el conductor, ¿no? Que no pegue acelerones o frenazos por uno de los parámetros que optimizan.
Data-driven approaches where you don't have to rely on a lot of hand-engineered costs, but also ground it in reality with physics-based checks. Now, a lot of what I described was with respect to the agents we could observe in the scene, but the same framework extends to objects behind occlusions.
Vale, mira.
We use the video feed from
Este es el Occupancy Map. Fijaos qué guapo. Que esto lo hemos visto antes también en el robot. Como con las cámaras se genera ese mapa. Cámaras 2D, recordemos. Aquí no hay LiDAR.
To generate what we call as ghost objects, which you can see on the top left. Now, if you model the spawn regions and the state transitions of these ghost objects correctly, if you tune your control response as a function of their existence like
Fijaos, claro, cuando cruza un coche, como estás prediciendo cuál es el Occupancy Map, aquí toda esta región sería una zona no visible. Entonces la incertidumbre en esta zona pues aumenta. Y ahora nos van a hablar de justamente esa parte, ¿no? Del occupancy.
Hey guys, my name is Phil. I will share the details of the occupancy network we built over the past year. This network is our solution to model the physical world in 3D around our cars. And it is currently not shown in our customer-facing visualization. And what you will see here is the raw network output from our internal dev tool. The occupancy network takes video streams of all our 8 cameras as input, produces a single unified volumetric occupancy in vector space directly.
Fijaos,
For every 3D location around our
a partir de 4 cámaras consigue predecir pues un mapa de ocupación bastante bueno.
It is capable of predicting obstacles that are occluded instantaneously.
Que no solo es detectar que hay objetos, sino localizarlos bien en ese espacio tridimensional, en ese espacio vectorial.
Car, pedestrian, and road debris, as color-coded here.
Fijaos, ¿eh?
Occupancy flow is also predicted for motion.
Hostia, cuidado tú.
Since the model is a generalized network, it does not tell static and dynamic objects explicitly. It is able to produce and model the random motions such as a swerving trainer here. This network is currently running in all Teslas with FSD computers, and it is incredibly efficient, runs about every 10 milliseconds with our neural net accelerator.
Que esto funciona ya en los coches de Tesla y va a 10 milisegundos.
First, we rectify each camera images with the camera calibration. And the images were
cogen el input de cada cámara, lo rectifican.
It's actually not the typical 8-bit RGB image. As you can see from the first image on top, we're giving the 12-bit raw photon count image to the network. Since it has 4 bits more information, it has 16 times better dynamic range, as well as reduced latency, since we don't have to run ISP in the loop anymore. We use a set of reglets and FPNs as a backbone to extract image space features. Next, we construct a set of 3D position query along with the image space features as keys and values fit into an attention module. The output of the attention module is high-dimensional spatial features. These spatial features are aligned temporally using vehicle odometry.
De nuevo, todo esto lo explicaron el año pasado con más detalle, ¿no? Y este año están pasando con más alto nivel.
Deconvolution to produce the final occupancy and occupancy flow output. They're formed as fixed-size voxel grid.
Pero todo esto es la arquitectura que montó Carpazzi.
In order to get a higher resolution, we also produce per voxel feature maps, which we feed into MLP with 3D spatial point queries to get position and semantics at any arbitrary location.
Rápidamente, lo paro. Esta primera parte coge los inputs, las cámaras, los pasan por redes que extraen patrones. Tiene pinta una red convolucional, pero que tiene... las regnes, no me acuerdo exactamente qué tenía de diferente, pero bueno, podemos pensar en una arquitectura convolucional de este tipo combinada con parte de atención. Esto de aquí utilizaban una especie de predicción del movimiento de la trayectoria del coche para, yo entiendo, aprovechar, ¿no?, el aprendizaje en cada caso, y teniendo también la dinámica del coche, pues se puede conseguir aprovechar más la información que ha aprendido en la fase anterior. Y luego esto lo utiliza para generar pues el volumen ya final, ¿no? El volumen del espacio. Que yo no sé si en este punto aquí utilizan algo parecido a NERF, porque esto de MLP me puede pegar que sea el Multilayer Perceptron. Le meten, o sea, generan como con las capas de convolucionales. Ya predicen como el volumen. Entiendo que estos serán a lo mejor 3D. No lo sé, habría que verlo más en detalle. Pero bueno, todo esto es para finalmente generar todo lo que hemos visto antes del mapa tridimensional con voxeles.
After knowing the model better, let's take a look at another example. Here we have an articulated bus parked on the right side of the road, highlighted as an L-shaped voxel here. As we approach, the bus starts to move. The front of the car turns blue first, indicating the model predicts the front of the bus has a non-zero occupancy flow. And as the bus keeps moving, the entire bus turns blue. And you can also see that the network predicts the precise curvature of the bus. Well, this is a very complicated problem for traditional object detection network.
El comentario de Ketji, de Guille, que es muy fino, ¿eh? Si lo pensáis, la hora del evento estará relacionada con la zona horaria donde necesitan ingenieros, poco interés por Europa. Ojo, ¿eh?
Besides the voxel grid, the occupancy network also produces a drivable surface. The drivable surface has both 3D geometry and semantics. They are very useful for control, especially on hilly and curvy roads. The surface and the voxel grid are not predicted independently. Instead, the voxel grid actually aligns with the surface implicitly. Here, we are at a hill crest where you can see the 3D geometry of the
vale, que no solo predice la occupancy, no solo predice este mundo voxelizado, sino también produce como el plano de la carretera.
As you can also see, the voxel grid aligns with the surface consistently. Besides the voxels and the surface, we're also very excited about the recent breakthrough in neural radiance field, or NERF. We're looking into both incorporate some of the light features into occupancy network training,
no lo estáis viendo
as well as
porque creo que
using
estoy
our network
solapando.
Output as the input state for NERF. As a matter of fact, Ashok is very excited about this.
El output de los volúmenes se utiliza también para entrenar a un estado NERF, que eso está bastante guapo.
These NERFs, because I think the academia is building a lot of these foundation models for language, using like tons of large data sets for language. But I think for vision, NERFs are going to provide the foundation models for computer vision, because they are grounded in geometry, and geometry gives us a nice way to supervise these networks and frees us of the requirement to define an ontology. And the supervision is essentially free because you just have to differentially render these images.
Es chulo esto que está diciendo, ¿eh?
This occupancy network idea where images come in and then the network produces a consistent volumetric representation of the scene that can then be differentially rendered into any image that was observed. I personally think is a future of computer vision, and we do some initial work on it right now, but I think in the future, both at Tesla and in the academia, we will see that these combination of one-shot prediction of full volumetric occupancy will be the future. That's my personal bet.
O sea, han cogido y le han dicho, oye, que también hemos puesto Nerf, porque aquí el amigo, el colega, ha hecho su proyecto de fin de semana con Nerf y ahora nos va a hablar de por qué lo usa, ¿no? Y ha dicho una cosa muy guapa que es, al igual que tenemos modelos fundacionales para texto, que son estos conceptos de transformers que predicen secuencias, modelos autorregresivos, que son capaces de generar texto muy realistas y sabemos que sirven para eso, pero para muchas otras tareas en el ámbito del texto, según su opinión, cree que estos modelos NERF en un futuro van a ser el esquema de modelo fundacional similar para todo lo que tenga que ver con imágenes, ¿no? Porque están basados en geometría y puede ser un punto de partida mucho más interesante para que a partir de esa geometría aprendida de muchísimas imágenes te puedas aplicar ahí un montón de tareas. Y esto es súper interesante porque quien haya seguido la actualidad que hemos compartido en Twitter estos días, habréis visto lo de Text to 3D, de cómo han creado, a partir de un Stable Diffusion que genera imágenes 2D que luego se entrena para NERF, han creado un sistema que te genera cosas en 3D al momento y usando la tecnología NERF. Así que está bastante encaminado este hombre, ¿eh? Tenemos vídeos en el canal sobre NERF. Pero bueno, básicamente es este sistema que tú le puedes meter un montón de imágenes en 2 dimensiones y una red neuronal aprende a generar un espacio tridimensional de él. Ahora vamos a ver algún ejemplo aquí. Esto es, ¿no?
Focusing on getting perfect RGB reprojection in image space, our primary goal here is to accurately represent the world in 3D space for driving. And we want to do this for all our fleet data all over the world, in all weather and lighting conditions. And obviously, this is a very challenging problem, and we're looking for you guys to help. Finally, the occupancy network is trained with large auto-labeled dataset without any human in the loop. And with that, I'll pass to Tim to talk about what it takes to train this network.
Thanks, Phil.
Cosa mía, hay mucha gente de India en industrias tecnológicas. Bueno, fíjate los SEOs de Microsoft,
so we've seen a couple of videos, 4 or 5. I think and care more and worry more about a lot more clips than that. So we've been looking at the occupancy networks just from Phil. Just Phil's videos. It takes 1.4 billion frames to train that network, what you just saw. And if you have 100,000 GPUs,
¿cómo han entrenado las redes que hemos visto hasta ahora? Pues con un huevo de vídeos que tienen y es la ventaja competitiva que tiene Tesla frente a todo el mundo.
Time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we've built in-house 3 supercomputers comprising of 14,000 GPUs.
14,000
GPUs,
GPUs,
10,000 GPUs for training and around 4,000 GPUs for auto-labeling. All these videos are stored in 30 petabytes of a distributed, managed video cache. You shouldn't think of our data sets as fixed, let's say, as you think of your ImageNet or something, with like 1 million frames. You should think of it as a very fluid thing. So we've got 500,000 of these videos flowing in and out of these clusters every single day. And we track 400,000 of these kind of Python video instantiations every second. So that's a lot of calls. We're going to need to capture that in order to govern the retention policies of this distributed video cache. So underlying all of this is a huge amount of infra, all of which we build and manage.
Toda la infraestructura que tienen montada para poder entrenar todo esto.
You cannot just buy, 14,000 GPUs and then 30 petabytes of flash.
Fijaos que esto es una conferencia de pasando por todos los detalles técnicos de la empresa para hablaros a vosotros, ingenieros.
What you actually typically want to do is you want to take your accelerator, So that could be the GPU or Dojo, which we'll talk about later. And because that's the most expensive component, that's where you want to put your bottleneck. And so that means that every single part of your system is going to need to outperform this accelerator. And so that is really complicated. That means
Interesante esto que ha dicho, ¿no? Si la GPU es el componente más caro, te interesa que ese sea el cuello de botella para tener ese recurso aprovechado al 100% y que el resto de recursos tienen que estar funcionando por encima de las GPUs.
But then you need to do so across hundreds or thousands of GPU in a reliable way, in lockstep, and in a way that's also fast. So you're also going to need an interconnect. Extremely complicated. We'll talk more about Dojo in a second. So first, I want to take you through some optimizations that we've done on our cluster.
Creo que se dirigen más los inversores que los ingenieros. No lo creo. No me parece esto una charla para inversores.
That's why we needed to go end-to-end from the storage layer down to the accelerator and optimize every single piece of that. Because we train on the photon count videos that come directly from our fleet, we train on those directly. We do not post-process those at all. The way it's just done is we seek exactly to the frames we select for our batch. We load those in, including the frames that they depend on. So these are your iframes or your key frames. We package those up, move them into shared memory, move them into a double buffer on the GPU, and then use the hardware decoder that's on the accelerator to actually decode the video. So we do that on the GPU natively. And this is all in a very nice PyTorch extension. Doing so unlocked more than 30% training speed increase for the occupancy networks and freed up basically the whole CPU to do any other thing. You cannot just do training with just videos. Of course, you need some kind of a ground truth. And that is actually an interesting problem as well. The objective for storing your ground truth is that you want to make sure you get to your ground truth that you need in the minimal amount of file system operations and load in the minimal size of what you need in order to optimize for aggregate cross-cluster throughput. Because you should see a compute cluster as one big device which has internally fixed constraints and thresholds. So for this, we rolled out a format that is native to us that's called small. We use this for our ground truth, our feature cache, and any inference outputs. So a lot of tensors that are in there. And so just a cartoon here, let's say these are is your table that you want to store, then that's how that would look.
Te estoy tomando nota, ¿no? Esto entra para examen, amigos.
So what you do is you take anything you'd want to index on. So for example, video timestamps, you put those all in the header so that in your initial header read, you know exactly where to go on disk. Then if you have any tensors, you're going to try to transpose the dimensions to put a different dimension last as the contiguous dimension, and then also try different types of compression. Then you check out which one was most optimal, and then store that one. This is actually a huge tip if you do feature caching. Unintelligible output from the machine learning network, rotate around the dimensions a little bit, you can get up to 20% increase in efficiency of storage. Then when you store that, we also order the columns by size so that all your small columns and small values are together, so that when you seek for a single value, you're likely to overlap with a read on more values.
Todo eso nos están contando todos los trucos y recursos que utilizan para optimizar el espacio que ocupan en memoria, tal. Está guapo, pero hostia. Claro, tú le pones esto a un inversor y te dice... Okay.
We now train our occupancy networks twice as fast just because it's twice as efficient. And now if we add in a bunch more compute and go parallel, we can now train this in hours instead of days. And with that, I'd like to hand it off to the biggest user of compute, John.
Esta señora era inversora. He dicho, bueno, hasta luego. Me voy.
Hi, everybody. My name is John Emmons. I lead the Autopilot vision team. I'm going to cover two topics with you today. The first is how we predict lanes, and the second is how we predict the future behavior of other agents on the road. In the early days of Autopilot, we modeled the lane detection
Este es Autopilot en su primera versión. Bueno, sus primeras versiones.
Our network was super simple, though. In fact, it was only capable of predicting lanes from of a few different kinds of geometries. Specifically, It would segment the eagle lane, it could segment adjacent lanes, and then it had some special casing for forks and merges. This simplistic modeling of the problem worked for highly structured roads like highways. But today we're trying to build a system that's capable of much more complex maneuvers.
Qué guapo.
Specifically, we want to make left and right turns at intersections, where the road topology can be quite a bit more complex and diverse. When we try to apply this simplistic modeling of the problem here, it just totally breaks down.
Este es el sistema que tenían de modelado de carreteras y
What we're
rutas
trying to do here is to predict the sparse set of lane instances
anterior.
and their connectivity. And what we want to do is to have a
Que creo que se
neural network
calculaba,
that
o sea, se
predicts this
predecía
graph,
directamente sobre las
where the
imágenes 2D,
nodes are the lane
no
segments,
se proyectaban
and the edges
sobre
encode the connectivities
el
between
espacio
these lanes.
vectorial, no era tridimensional. El que nos van a enseñar ahora,
So what we have is our lane detection neural network.
exacto, vale, esto lo vimos el año pasado,
It's
está
made up
chulo.
of 3 components. In the first component, we have a set of convolutional layers, attention layers, and other neural network layers
Lo que hemos visto
that
antes, ¿no?
encode
Capas
the
convolucionales,
video streams from our 8
transformers.
cameras on the vehicle and produce a rich visual representation. We then enhance this visual representation with a coarse road level map data, which we encode with a set of additional neural network layers that we call the lane guidance module. This map is not an HD map, but it provides a lot of useful hints about the topology of lanes inside of intersections, the lane counts on various roads, and a set of other attributes that help us. The first 2 components here produced a dense tensor that sort of encodes the world. But what we really want to do is to convert this dense tensor into a sparse set of lanes and their connectivities. We approach this problem like an image captioning task, where the input is this dense tensor, and the output text is predicted into a special language that we developed at Tesla for encoding lanes and their connectivities. In this language of lanes, the words and tokens are the lane positions in 3D space. In the ordering of the tokens, and predicted modifiers on the tokens encode the connective relationships between these lanes.
Hostia. Vale. Hasta aquí todo correcto. Es decir, de las cámaras sacan la información, generan magia aquí, procesan cosas y generan como una especie de tensor tridimensional donde está la información como si fuera comprimida, ¿no? Un vector, en este caso un tensor tridimensional, ¿vale? Y luego esto lo decodifican, han dicho, utilizando un autoregressive decoder, que esto sería como un GPT-3. Es decir, usando esto como input, esta información, este tensor tridimensional denso, condicionado a eso, aquí empiezan a hacer un proceso como si fuera GPT-3 generando. ¿Pero qué genera? No genera palabras, evidentemente. Genera un lenguaje que ellos han han creado en Tesla, para que ese lenguaje se pueda decodificar como los diferentes atributos de carretera y todo esto. Madre mía. Es súper curioso como el esquema este de modelos autorregresivos que predicen tokens, y esos tokens si los interpretas, pues por ejemplo lo que vimos con Gato, ¿no? Los interpretas como una secuencia de acciones, pues puedes generar un modelo que juega videojuegos, ¿no? Como se está convirtiendo en el estándar para muchos de los modelos que estamos viendo hoy en día. Súper curioso.
By modeling the task as a language problem, we can capitalize on recent autoregressive architectures and techniques from the language community for handling the multimodality of the problem. We're not just solving the computer vision problem at Autopilot, we're also applying the state-of-the-art in language modeling and machine learning more generally. I'm now going to dive into a little bit more detail of this language component.
Vamos, mira.
What I have depicted on the screen here is a satellite image which...
Nos va a enseñar ahora el lenguaje este, ¿no? Que han generado y el modelo de lenguaje, que es lo que predice. Muy loco.
Sort of represents the local area around the vehicle. The set of nodes and edges is what we refer to as the lane graph, and it's ultimately what we want to come out of this neural network. We start with a blank slate. We're going to want to make our first prediction here at this green dot.
Vale. Nosotros estamos aquí, ¿vale? Pensad que estamos aquí abajo, en el punto verde.
This green dot's position is encoded as an index into a coarse grid which discretizes the 3D world. Now, we don't predict this index directly, because it would be too computationally expensive to do so. There's just too many grid points, and predicting a categorical distribution over this has both...
Vale, pues estamos en el punto verde y lo que dicen es vamos a discretizar el espacio tridimensional como una rejilla, pero que esto es muy ineficiente porque veis que hay un montón de cuadraditos que, a ver, por ejemplo, aquí no te interesa predecir nada, ¿no? Entonces yo creo que aquí es donde va a entrar el Occupancy Map para quitar muchos de estos cuadrados.
Both implications at training time and test time. So instead what we do is we discretize the world coarsely first. We predict a heat map over the possible locations, and then we latch in the most probable location. Condition on this We then refine the prediction
Vale.
and get the precise point.
Vale, utilizan multiresolución de la rejilla para simplemente centrarse en la que están.
Now we know where the position of this token is. We don't know its type. In this case, though, it's the beginning of a new lane. So we predict it as a start token. And because it's a start token, there's no additional attributes in our language.
Vale, entonces aquí es como en cada nivel lo que se predice es en la rejilla que hemos visto inicialmente, pues estamos en el index 18. En la segunda rejilla, dentro de la casilla 18, ¿en cuál estamos? En la 31. Topology Type Predictor, no me he quedado con qué es, Start. Entonces aquí se va prediciendo cada cosa. Estos son los tokens que predice el modelo del lenguaje que ellos han entrenado para ir prediciendo todo este lenguaje, ¿no? De la carretera. Me parece súper loco. Pero está guapo.
We then take the predictions from this first forward pass and we encode them using a learned positional embedding, which produces a set of tensors that we combine together, which is actually the first word in our language of lanes. We add this to the first position in our sentence here.
¿Vale? Esa información la convierten a vectores densos a través de capas de embedding, las concatenan todos y ese es el primer token de su modelo, o sea, de su predicción.
We then continue this process by predicting the next lane point in a similar fashion. Now this lane point is not the beginning of a new lane, it's actually a continuation of the previous lane. So it's a continuation token type. Now it's not enough just to know that this lane is connected to the previously predicted lane. We want to encode its precise geometry, which we do by regressing a set of spline coefficients.
Joder, macho.
We then take this lane, we encode it again, and add it as the next word in the sentence.
Vale, lo que han codificado ahora es, mira, el siguiente punto de carretera, este punto amarillo, es la continuación del punto verde, que además no es una línea recta, sino que es una curva, entonces colocan la coordenada, el index 9, la casilla 22, es una continuación de la lane, de la verde que teníamos anteriormente, y además aquí guardan una especie de coeficientes que no se está viendo por la barra, pero que es la que hace que el spline pues sea curvo, ¿no? Y con esto ya tienen el segundo. Yo flipo. Pero no son nuevas arquitecturas de IA, son las arquitecturas que ya tenemos utilizadas de forma diferente.
Now, it's not topologically connected to that pink point. It's actually forking off of that green point there. So it's got a fork type. And fork tokens actually point back to previous tokens from which the fork originates. So you can see here the fork point predictor is actually the index 0. So it's actually referencing back to tokens that it's already predicted, like you would in language. We continue this process over and over again until we've enumerated all of the tokens in the lane graph, and then the network predicts the end of sentence token.
Yeah, I just want to note that the reason we do this is not just because we want to build something complicated. It almost feels like a Turing-complete machine here with neural networks, though, is that we tried simpler approaches. For example, trying to just segment the lanes along the road or something like that. But then the problem is when there's uncertainty, say you cannot see the road clearly, and there could be 2 lanes or 3 lanes, and you can't tell, a simple segmentation-based approach would just draw both of them. It's kind of a 2.5 lane situation. And the post-processing algorithm would hilariously fail when the predictions are such.
Yeah, and the problems don't end there. I mean, you need to predict these connective lanes inside of intersections, which it's just not possible with the approach that Ashok's mentioning, which is why we had to upgrade to this sort of...
Yeah, when it overlaps like this, segmentation would just go haywire, but even...
O sea, lo que entiendo aquí al final es lo que están haciendo es lo siguiente. Lo que acaban de decir, ¿no? Si tú intentas darle sentido a todas estas carreteras, a todos estos carriles con segmentación, ¿no? Solo con la parte visual, se acaba perdiendo, ¿no? Porque hay cosas que son muy, muy intrincadas. Pero planteándolo esto como un problema o sea, como una secuencia con un código que puedes predecir de forma autorregresiva, es como darle la oportunidad a la inteligencia artificial de entender que, oye, este patrón de cruce va a estar muy repetido en la ciudad, no va a ser una única estructura. Por muy complejo que sea, la inteligencia artificial podría entender que, pues si aquí tienes un punto de carril y otro punto de carril, luego puede predecir que el siguiente token no va a estar hacia atrás, sino estará a lo mejor por aquí, ¿no? En este punto de aquí. Entonces, entiendo que esa es la lógica del modelo autorregresivo, que te permite condensar mucho mejor toda esa información de forma secuencial, pero wow. O sea, en la vida se me hubiera ocurrido plantear el problema de esta forma. Por eso yo soy youtuber y ellos son ingenieros de Tesla.
Even if you try very hard to put them on separate layers. It's just a really hard problem. But language just offers a really nice framework for getting a sample from a posterior as opposed to trying to do all of this in post-processing. But this doesn't actually stop for just Autopilot, right, John? This can be used for Optimus.
Yeah, I guess they wouldn't be called lanes, but you could imagine, sort of in this, stage here, that you might have sort of paths that sort of, encode the possible places that people could walk.
Que esto se puede utilizar para Optimus, están comentando, ¿no? Que al final aquí lo usan para carriles, pero puede servir para definir cualquier tipo de estado dentro de un entorno, dentro de un espacio. Ojo, aquí son casi las 5 de la mañana y os estoy contando todas estas cosas, ¿eh? Si no habéis dado a me gusta, like y todas estas cosas, creo que va tocando. 745 likes, somos el doble aquí, ¿eh? Si queréis mandar apoyo con tips, también podéis.
Okay, so I talked a little bit about lanes. I'm going to briefly touch on how we model and predict the future paths and other semantics on objects.
Con superchats.
So I'm just going to go really quickly through
mostrar
two examples.
apoyo.
The video on the right here, we've got a car that's actually running a red light and turning in front of us. What we do to handle situations like this is we predict a set of short time horizon future trajectories on all objects. We can use these to anticipate the dangerous situation here and apply whatever braking and steering actions required to avoid a collision. In the video on the right, there's two vehicles in front of us. The one in the left lane is parked. Apparently it's being loaded, unloaded. I don't know why the driver decided to park there. But the important thing is that our neural network predicted that it was stopped, which is the red color there. The vehicle in the other lane, as you notice, also is stationary. But that one's obviously just waiting for that red light to turn green. So even though both objects are stationary and have zero velocity, it's the semantics that is really important here, so that we don't get stuck behind that
200 likes, bien.
Predicting
Gracias, Gerardo. Muchas gracias por el
practical
cafecito.
problems when trying to build a real-time system. We need to maximize the frame rate of our object detection stack so that Autopilot can quickly react to the changing environment. Every millisecond really matters here. To minimize the inference latency, our neural network is split into two phases. In the first phase, we identify the locations in 3D space where agents exist.
Muchas gracias, Marcelo, por ese
We
apoyo.
then pull out tensors at those 3D locations, append it with additional data that's on the vehicle, and then we do the rest of the processing. This sparsification step allows the neural network to focus compute on the areas that matter most, which gives us superior performance for a fraction of the latency cost. So putting it all together, the Autopilot vision stack predicts more than just the geometry and kinematics of the world.
Es que es flipante, ¿eh? O sea, todo lo que está calculando el coche en tiempo real es una brutalidad.
I'm now going to hand things off to Sri, who will tell us how we run all these cool neural networks on our FSD computer. Thank you.
Es brutal. Otro inversor que se va.
Hi everyone, I'm Sri. Today I'm going to give a glimpse of what it takes to run these FSD networks in the car and how do we optimize for the inference latency. Today I'm going to focus just on the FSD lanes network that John just talked about. So when we started this track, we wanted to know if we can run this FSD lanes network natively on the TRIP engine, which is our in-house neural network accelerator that we built in the FSD computer. When we built this hardware, we kept it simple and we made sure it can do one thing ridiculously fast, dense dot products. But this architecture is auto-regressive and iterative, where it crunches through multiple attention blocks in the inner loop, producing sparse points
Ahora
directly
que nos
at
están hablando de cómo tienen que optimizar para poder ejecutar en tiempo real estos modelos dentro del ordenador del coche, ¿no? Al final tienes un modelo autorregresivo que iterativamente tiene que ir prediciendo el siguiente token.
So the network predicts the heat map of most probable spatial locations of the point. Now we do a argmax and a one-hot operation, which gives the one-hot encoding of the index of the spatial location.
Primero saca el heatmap con diferentes valores, luego hacen un argmax, es decir, sacan el valor máximo del vector. Muchas gracias, Marcelo. Muchas gracias por el apoyo.
On TRIP, we actually built a lookup table in SRAM, and we engineered the dimensions of this embedding such that
el vector con el argmax selecciona de una tabla de embeddings, selecciona el cubito
we also wanted
Donde
to
está marcado el 1,
store
pues
this
saca el
embedding
cubo, es como
into
una
a
especie de
token cache
selección de una
so
tabla.
that we don't recompute this for every iteration, rather reuse it for future point prediction. Again, we pulled some tricks here where we did all these operations just on the dot product engine. It's actually cool that our team found creative ways to map all these operations on the trip
Gracias,
engine
Marcelo.
in ways that were not even imagined when this hardware was designed.
Bueno, hay que echar la información de los tokens para poder reutilizarlos para optimizar todo. Es todo la red que nos han explicado antes, cuáles son los pasos y cómo ellos lo están optimizando para poder ejecutarlo en tiempo real, ¿no? Aquí cada milisegundo cuenta.
As well as to optimize performance. All of these things helped us run this 75 million parameter model just under 10 milliseconds of latency, consuming just 8 watts of power. But this is not the only architecture running in the car. There are so many other architectures, modules, and networks
Claro, este es uno
need to run in
de
the
los
car.
modelos que se ejecutan, pero hay
To give a sense
muchísimos
of
modelos
scale,
ejecutándose.
there are about a billion parameters of all the networks combined,
En total-
producing around 1,000 neural network signals.
En total, todos los modelos
So, we
suman
need to
1000
make sure
millones,
we optimize them
1000 millones de
jointly
parámetros.
and such that we maximize the
Muchas gracias,
compute
Lucy.
utilization, throughput, and minimize the latency. So we built a compiler just for neural networks that shares the structure to traditional compilers. As you can see, it takes the massive graph of neural nets with 150K nodes and 375K connection, takes this thing, partitions them into independent subgraphs, and compiles each of those subgraphs natively for the inference devices. Then we have a neural network linker which shares the structure to traditional linker, where we perform this link time optimization. There we solve an offline optimization problem with compute memory and memory bandwidth constraints, so that it comes with an optimized schedule that gets executed in the car.
O sea, que sacan todo como la planificación de ejecución, la optimizan y luego eso es ese es el planificador de ejecución que utilizan dentro del coche. Todo tiene que estar optimizado, todo.
To get 100 TOPS of compute utilization, we need to optimize across all the layers of software, right from tuning the network architecture, the compiler, all the way to implementing a low latency, high bandwidth RDMA link across both the SoCs, and in fact, going even deeper to understanding and optimizing the cache coherent and non-coherent data paths of the accelerator in the SoC. This is a lot of optimization at every level in order to make sure we get the highest frame rate, and as every millisecond counts here. And this is just the visualization of the neural networks that are running in the car. This is our digital brain, essentially.
Qué guapo.
As you can see, these operations are nothing but just the matrix multiplication, convolution, to name a few.
Este es el cerebro del coche, ¿no? Lo han puesto así con un gráfico chulo, que no significa nada, también te digo. Pero que está chulo de ver, son como todas las operaciones conectadas. No sé en base a qué, pero ok, está bonito, está guapo el metaverso.
Thank you, Sri. Hi, everyone. I'm Yegan Zhang, and I'm leading geometric vision at Autopilot. So, yeah, let's talk about auto labeling. So we have several kinds of auto labeling frameworks to support.
Vale, ahora nos van a hablar de el autoetiquetado, el autolabeling.
LanesNet here. So to successfully train and generalize this network to everywhere, we think we went tens of millions of trips from probably 1 million intersection or even more.
Vale, lo que vamos a ver ahora, lo paro para no solaparme, es el proceso, si no me equivoco, de autoetiquetado. Es decir, ya no estamos hablando de lo que ve el coche o ejecuta el coche en el propio interior, sino lo que se ejecuta en los superordenadores de Tesla para hacer el entrenamiento de los modelos que luego se despliegan en el coche. Entrenamientos que requieren entender, estructurar un montón de clips de vídeos que ellos han ido recopilando y que una parte de esos datos tienen que estar etiquetados. Claro, etiquetar esos datos manualmente es una locura, es imposible. Van a hablarnos de los sistemas de autoetiquetado, de cómo han creado pues, otros algoritmos, otras técnicas para hacer esto automáticamente. Por cierto, OpenAI este año ha sacado un par de trabajos bastante chulos. Uno que aprendí a jugar al Minecraft y otro es el de Whisper, que muestran dos esquemas de entrenamiento con autoetiquetado, bastante guapo.
So then how to do that? So it is certainly achievable to source sufficient amount of
No, como
trips,
puedes
because
etiquetar, por
we already
ejemplo, más de un
have, as
millón
Kim
de
explained earlier,
intersecciones.
We already have like 500,000 trips per day cache rate. However, converting all those data into a training form is a very challenging technical problem. To solve this challenge, we've tried various ways of manual and auto labeling. So from the first column to the second, from the second to the third, each advance provided us nearly 100x improvement in throughput. But still, we run an even better auto labeling machine that can provide us good quality, diversity, and scalability.
Muchas gracias, Patricio. Muchas gracias por ese apoyo.
To meet all these requirements,
Estáis aportando, estáis...
huge amount of engineering effort required.
Muchas gracias. Se
We
agradece.
developed a new auto labeling machine powered by multi-trip reconstruction. So this can replace 5 million hours of manual labeling with just 12 hours on cluster for labeling 10,000 trips. So how we solved? There are 3 big steps. The first step is high precision trajectory and structure recovery by multi-camera, visual inertial odometry. So here, all the features, including ground surface, are inferred from videos by neural networks, then tracked and reconstructed in the vector space. So
Vale, aquí utilizan algoritmos de redes neuronales de las que conocemos todos para hacer la predicción de, para cada cámara, la posición de cada elemento, suelo, coches, tal, y luego lo reconstruyen todo en el espacio tridimensional.
the typical drift rate of this trajectory in car is like 1.3 centimeter per meter and 0.45 milliradian per meter, which is pretty decent considering its compact compute requirement. Then the recovered surface and road details are also used as a strong guidance for the later manual verification.
Fijaos que lo que estamos viendo aquí ahora son procesamientos más avanzados que lo que estábamos viendo antes, porque esto ya lo pueden hacer offline en sus centros de computación. Esto ya no se tiene que ejecutar en tiempo real en el coche. Esto aquí pueden meter modelos de la hostia. Y vamos a ver nerf aquí segurísimo, ya veréis.
So the video shows
Qué guapo,
how
tío.
the previously shown trip is reconstructed and aligned with other
Mirad,
trips.
mirad, qué
Basically,
guapo,
other
cómo
trips
se...
from different vehicles,
Como la
different
flota de diferentes
So
coches
this is done by multiple
reconstruye
intersteps like
toda la ciudad.
course alignment, pairwise matching, joint optimization,
El nuevo GTA
and
aquí,
further surface refinement. In the end, the human analyst comes in and finalizes the label. So each habit steps are already fully parallelized on the cluster. So the entire process
Es que tienen
takes just a
a
couple of
humanos etiquetando todos estos datos en el momento en el que tienes a toda una flota de conductores con vehículos de Tesla
auto-labeling the new trips.
circulando por las calles.
So, here we use the same
Bueno, están haciendo el proceso de recopilación de datos, luego el etiquetado es automático, pero ya me entendéis.
And each new trip. So it's much simpler than fully reconstructing all the clips altogether. That's why it only takes 30 minutes per trip to auto-label instead of several hours of manual labeling. And this is also the key of scalability of this machine. This machine easily scales as long as we have available compute and trip data. So about 50 trips were newly auto-labeled from this scene, and some of them are shown here. So 53 from different vehicles. So this is how we capture and transform the space-time slices of the world into the network supervision.
Yeah, one thing I'd like to note is that Jagan just talked about
Si ya solo este dataset que tiene Tesla tiene un valor de la hostia.
Almost every task that we do, including our planner.
Muchas gracias, Matías. Un abrazo
Fully automatic,
desde
no
Uruguay, qué
humans
guay.
involved. For example, for objects,
Y rima.
all the kinematics, the shapes, the futures, everything just comes from auto labeling. And the same is true for occupancy too. And we have really just built a machine around this.
Yeah, so if you can go back one slide.
Ojo, ojo, que se vienen arriba.
One more. It says parallelized on cluster. So that sounds pretty straightforward, but it really wasn't. Maybe it's fun to share how something like this comes about. So a while ago, we didn't have any auto labeling at all. And then someone makes a script, it starts to work, it starts working better until we reach a volume that's pretty high and we clearly need a solution. And so there were two other engineers in our team who were like, hey, that's an interesting thing, what we needed to do was build a whole graph of essentially Python functions that would need to run one after the other. First you pull the clip, then you do some cleaning, then you do some network inference, then another network inference, until you finally get this. So you need to do this at a large scale. So I tell them, we probably need to shoot for 100,000 clips per day, or like 100,000 items. That seems good. And so the engineers said, well, we can do a bit of Postgres and a bit of elbow grease. We can do it. Meanwhile, we are a bit later, and we're doing 20 million of these functions every single day. Again, we pull in around 500,000 clips, and on those, we run a ton of functions, each of these, in a streaming fashion. And so that's kind of the back-end infra that's also needed to not just run training, but also auto-labeling.
Yeah, it really is like a factory that produces labels, and it's like production lines, yield, quality, inventory, like all of the same concepts apply to this label factory.
Nada, bueno, ha comentado eso, ¿no? Como originalmente esto era manual y al final los ingenieros fueron trabajando en el problema, desarrollando diferentes funciones de Python y al final es como un pipeline, una secuencia de funciones que funciona como una fábrica de generar etiquetas. Qué guapo. Muchas gracias, Equinoccio. ¿En cuántos años veremos un Tesla Bot en producción? No creo que tarden mucho en sacar 3-4 años. Yo creo que vamos a tener un primer prototipo vendible. Al igual que Boston Dynamics tiene a Spot, por ejemplo. Yo creo que 3-4 años es razonable, por lo que han enseñado hoy. Pero no para el ámbito doméstico, sino para fábricas.
Thank you, Jagan. My name is David, and I'm going to talk about simulation. So simulation plays a critical role in providing data that...
Vale, hemos visto la primera forma de generar datos, que es con estos sistemas autoetiquetados. La segunda forma, que es gratuita, es... Bueno, gratuita, entendedme. Podemos generar datos infinitos, pues con... Esto lo hemos visto mucho en los directos de NVIDIA, generando copias de la realidad, con simulaciones.
That is difficult to source and or hard to label. However, 3D scenes are notoriously slow to produce.
Lo bueno de una simulación es que te permite simular cualquier locura.
Simulated scene playing behind me. A complex intersection from Market Street in San Francisco. It would take 2 weeks for artists to complete. And for us, that is painfully slow. However, I'm going to talk about using Jagan's automated ground truth labels along with some brand new tooling that allows us to procedurally generate this scene and many like it in just 5 minutes. That's an amazing 1,000 times faster than before. So let's dive in to how a scene like this is created.
Me los quito rápido.
We start by piping the automated ground truth labels into our simulated world creator tooling inside the software Houdini. Starting with road boundary labels, we can generate a solid road mesh and retopologize it with the lane graph labels. This helps inform important road details like crossroad slope and detailed.
Como a partir de las líneas originales están simulando, están generando proceduralmente toda la ciudad. Qué guapo. Y ahora con Stable Diffusion esto lo tenéis más fácil. Todo esto es procedural, ¿eh? Qué guapo. Pero es que con lo que ha salido esta semana de generar objetos 3D o objetos o texto a imagen también con Stable Diffusion, estos simuladores se pueden volver mucho más potentes en 1 año, 2 años. Porque ya no tienes que tener una librería de assets, ya puedes meter ahí objetos a cholón.
Important information like number of lanes and even get accurate street names on the signs themselves. Next, using lane graph, we can determine lane connectivity and spawn directional road markings on the road and their accompanying road signs. And finally, with lane graph itself, we can determine lane adjacency and other useful metrics to spawn randomized traffic permutations.
Qué pasada. Fijaros que la estructura principal, lo que veis en verde, es lo que han utilizado para condicionar el resto de la generación y son los gráficos de lanes, que no, de pistas, no sé cómo se traduce lane ahora, de carriles, ¿no? Que es lo que hemos visto antes que predice este modelo autorregresivo
can be as subtle
tipo
as
GPT-3.
object placement and random material swapping to more drastic changes.
Muchas gracias, Ricardo.
Entirely new biomes or locations
Ricardo, muchas gracias.
like urban,
Y David
suburban,
Moya.
or rural. This allows us to create infinite targeted permutations for specific
¿Cómo puede
ground
aportar un
truths
ingeniero
that we need
aeronáutico
for ground
en
truth
Tesla? Pues no
And
sabría
all this
decirte, no sé
happens within a click
exactamente
of a button.
cuál es vuestro expertise completo, pero
We
me
can
imagino
even
que
take
toda la
this
parte de
one step
aerodinámica
further by altering
seréis
our ground
útiles.
truth itself.
Y luego hay
Say
mucho
John
conocimiento
wants his
troncal
network to
que
pay more attention
es ingeniería,
to
¿no?
directional road markings to better detect an upcoming captive left turn lane. We can start to procedurally
Y la
alter
mujer de
our lane
rojo.
graph inside the simulator to
No
help
mires a la
focus-
mujer
to
de rojo.
create entirely new flows through this intersection to help focus the network's attention to the road markings to create more accurate predictions. And this is a great example of how this tooling allows us to create new data
Muy
that
fuerte.
could never be collected.
Y si solo con las líneas, entonces es súper
The true power
interesante.
of this tool is in its architecture and how we can run all tasks.
Perdón un momento. Es súper interesante porque si tú tienes el grafo que representa las líneas de trayectoria de la carretera, tú dices, oye, es que he detectado que mi vehículo cuando llega a un cruce con 4 carriles contra 3 carriles y a lo mejor hay una pista de tranvía, falla. Por algún motivo falla. Pues vamos a generar, no sé, 10.000 de estos carriles, de estas trayectorias en simulación y vamos a entrenar, vamos a generar datos artificiales y con esto vamos a ver si conseguimos solventar el problema.
In parallel to infinitely scale. So you saw the
Muchas gracias,
tile
Luismi.
tool in action, converting the ground truth labels
Muchas gracias por el apoyo.
to their counterparts.
Ojo, estáis apoyando un montón,
Next,
chicos.
we can use
Qué
our
guay.
tile extractor tool to divide this data into geohash tiles about 150 meters square in size. We then save out that data into separate geometry and instance files. This gives us a clean source of data that's easy to load and allows us to be rendering engine agnostic for the future. Then, using a tile loader tool, we can summon any number of those cache tiles using a geohash ID. Currently, we're doing about these 5x5 tiles or 3x3, usually centered around fleet hotspots or interesting lane
Aquí me he
graph
perdido, no sé
locations.
exactamente para qué es esta parte, pero bueno.
And the tile loader also converts these tile sets into U assets for consumption by the Unreal Engine and gives you a finished product from what you saw in the first slide.
Es como que crean una
This really
región del
sets us
mapa,
up
¿no?
for
Estos
size
tiles.
and scale. And as you can see on the map behind us, we can easily generate most of San
Mirad qué
Francisco's city
guapo.
streets.
Hostia,
This
GTA San
didn't take
Francisco. ¿eh?
years or even months of work, but rather 2 weeks by one person. We can continue
Dios.
to manage and grow all this data using our PDG network inside.
O sea que pueden generar toda la simulación de todo lo que veis en rojo, de todas estas regiones de San Francisco, lo han generado en 2 semanas con una persona. El nivel de simulación que hemos visto antes.
Tooling. This allows us to throw compute at it and regenerate all these tile sets overnight.
Qué fuerte.
This ensures all environments are of consistent quality and features, which is super important for training, since new ontologies and signals are constantly released.
No me lo creo. ¿Sí? ¿En serio? El simulador se llamaba Ground Truth Alterations, lo que en inglés significa GTA, que es un gran guiño. ¡Wow! Buenísima.
And now, to come full circle, because we generated all these tile sets from ground truth data, they contain all the weird intricacies from the real world, and we can combine that with the procedural, visual, and traffic variety to create limitless, targeted data for the network to learn from.
Claro. Y esto es donde
Next
cierras
concludes the
el,
section. I'll pass it to Kate to
cierras el
talk
bucle,
about
¿no?
how we
Ahora
can use
metes
all
un
this
coche
data
dentro de tu
to improve
simulación
Autopilot. Thank you.
con las cámaras y los sensores que tenga el Tesla y con eso generas los datos y el Ground Truth para poder entrenarlo. Datos gratis. Falta un detalle aquí, pero bueno.
Hi everyone, my name is Kate Park.
Falta un detalle que suele ser que en esta simulación se le añade una última capa con redes generativas, con modelos que cogen image to image para darle más realismo a la simulación, porque todavía se ve un poco artificial y siempre interesa aproximar la simulación lo más parecido a tu realidad, a cómo se ve en el mundo real, ¿no? Y esa última capa no la han puesto y el año pasado creo que sí estaba.
And I'm here to talk about the data engine, which is the process by which we improve our neural networks via data. We're going to show you how we deterministically solve interventions via data and walk you through the life of this particular clip. In this scenario, Autopilot is approaching a turn and incorrectly predicts that crossing vehicle as stopped for traffic.
Vale, lo último que nos van a enseñar es cómo consiguen a partir de los pilotos que tienen en carretera, es decir, la gente que está usando ya los coches de Tesla, cómo pueden generar un motor para extraer errores y sacar más datos de ese momento, ¿no? Pues aquí hay un fallo del coche que ha detectado mal al coche que está a la derecha.
We can curate this evaluation set without any engineering resources custom to this particular challenge case. To actually solve that challenge case requires mining thousands of examples like it, and it's something Tesla can trivially do. We simply use our data sourcing infra, request data, and use the tooling shown previously to correct the labels. By surgically targeting the mispredictions of the current model, we're only adding the most valuable examples to our training set. We surgically fixed 13,900 clips, and because those were examples where the current model struggles, we don't even need to change the model architecture. A simple weight update with this new valuable data is enough to solve the challenge case. So you see, we no longer predict that crossing vehicle as stopped, as shown in orange, but parked, as shown in red. In academia, we often see that people keep data constant, but at Tesla, it's very much the opposite. We see time and again that data is one of the best, if not the most deterministic lever to solving these interventions. We just showed you the data engine loop for one challenge.
Es una cosa curiosa, ¿no? Como en la academia, por lo general, los datasets son estáticos, no varían, ¿no? ImageNet es ImageNet, con sus errores y con sus aciertos. Pero que en Tesla ellos viven lo contrario, ¿no? Como sus datasets son cambiantes, van variando, van agregando datos, los van modificando, van corrigiendo. Y es interesante.
In fact, this year, we updated our vehicle movement signal 5 times. And with every weight update trained on the new data, we push our vehicle movement accuracy up and up. This data engine framework applies to all our signals, whether they're 3D, multicam video, whether the data is human-labeled, auto-labeled, or simulated, whether it's an offline model or an
Todo este es
online
el
model.
motor de datos, ¿no? Todo el sistema de simulación, etiquetado automático, corrección, todo esto genera un motor que yo creo que le da a Tesla uno de los grandes valores, y es la gran cantidad enorme de datos que tienen. Datos además estructurados, etiquetados, y que es con lo que nutren a sus modelos de entrenamiento que ya hemos visto antes, ¿no? Ya hemos visto modelos, hemos visto datos, y ¿qué nos falta ahora? Infraestructura de entrenamiento, el hardware, el supercomputador. Y aquí es donde está DOJO.
I run the custom silicon and low voltage teams at Tesla.
And my name is Ganesh Venkat. I run the DOJO program.
Thank you. I'm frequently asked, why is a car company building a supercomputer for training? And this question fundamentally misunderstands the nature of Tesla. At its heart, Tesla is a hardcore technology company. All across the company, people are working hard in science and engineering to advance the fundamental understanding and methods that we have available to build cars, energy solutions, robots, and anything else that we can do to improve the human condition around the world. It's a super exciting thing to be a part of, and it's a privilege to run a very small piece of it in the semiconductor group. Tonight we're going to talk a little bit about DOJO and give you an update on what we've been able to do over the last year. But before we do that, I wanted to give a little bit of background on the initial design that we started a few years ago.
DOJO.
When we got started, the goal
Recordemos
was to
que era
provide a
este
substantial
supercomputador
improvement to the training
modular que
latency
nos
for our
enseñaron el año
Autopilot
pasado.
team. Some of the largest neural networks they train today run for over a month, which inhibits their ability to rapidly explore alternatives and evaluate them. So, you know, a 30x speed up would be really nice if we could provide it at a cost competitive and energy competitive way. To do that, we wanted to build a chip with a lot of arithmetic units that we could utilize at a very high efficiency. And we spent a lot of time studying whether we could do that using DRAM, various packaging ideas, all of which failed. And in the end, even though it felt like an unnatural act, we decided to reject DRAM as the primary storage medium for this system and instead focus on SRAM embedded in the chip. SRAM provides unfortunately, a modest amount of capacity, but extremely high bandwidth and very low latency. And that enables us to achieve high utilization with the arithmetic units. Those choices.
Bueno, nos está explicando un poco las decisiones de diseño que han ido tomando, ¿no? Desde cambiar el tipo de RAM a su prioridad de meter unidades aritméticas.
We also don't have interrupts. The accelerator is a bare bones raw piece of hardware that's presented to a compiler, and the compiler is responsible for scheduling everything that happens in a deterministic way. So there's no need or even desire for interrupts in the system. We also chose to pursue model parallelism as a training methodology, which is not the typical situation. Most machines today use data parallelism, which consumes additional memory capacity, which we obviously don't have. So all of those choices led us to build a machine that is pretty radically different from what's available today. We also had a whole bunch of other goals. One of the most important ones was no limits.
Esta no se
So we
preparó la
wanted to build a
diapositiva.
compute fabric that would scale in an
Este dijo, yo voy
unbounded
a
way
pelo.
for the most part. I mean, obviously there's physical limits now and then, but pretty much if your model was too big for the computer, you just had to go buy a bigger computer. That's what we were looking for. Today, the way machines are packaged, there's a pretty fixed ratio of, for example, GPUs, CPUs, and DRAM capacity and network capacity. And we really wanted to disaggregate all that so that as models evolved, we could vary the ratios of those various elements and make the system more flexible to meet the needs of the Autopilot team.
Yeah, and it's so true, Pete, like no limits philosophy was our guiding star all the way. All of our choices were centered around that. And to the point that we didn't want traditional data center infrastructure to limit our capacity to execute these programs at speed. So that's why we integrated vertically.
Este hombre fue el que enseñó el año pasado los chips, me acuerdo.
Data center by
Todo
doing
orgulloso.
vertical integration of the data center.
Mucho procesador, poco micrófono, ¿eh?
New levels of efficiency. We could optimize power delivery, cooling, and as well as system management across the whole data center stack rather than doing box by box and integrating those boxes into data centers. And to do this, we also wanted to integrate early to figure out limits of scale for our software workload.
Está siendo dura esta parte, ¿eh? Aquí el sueño empieza a apretar, son las 5:15 de la mañana. Pero aguantamos. Hay 300 personas por aquí que no le han dado like todavía al directo.
And Rajiv Kurian will give you a glimpse of our compiler technology as well as go over some of our cool results.
Great. There you go.
Thanks, Pete. Thanks, Ganesh. I'll start tonight with a high-level vision of our system that'll help set the stage for the challenges and the problems we're solving, and then also how software will then leverage this for performance. Now, our vision for Dojo is to build a single unified accelerator, a very large one. Software would see a seamless compute plane with globally addressable, very fast memory, and all connected together with uniform, high bandwidth, and low latency. Now, to realize
Vale,
this,
este era
we need to use density
lo que enseñaron
to
el año
achieve
pasado, ¿no?
performance.
Que son sus tiles.
Now, we leverage
que son
technology
como,
to get this density in order to break levels of
cada uno de estos son los procesadores y tienen como un conjunto de procesadores y todo
Now,
metido en
silicon
esta,
technology has used
no me
this
sale la
and
palabra
done this
tile en
for
español,
decades.
casilla,
Chips have followed
que es
Moore's
modular,
law
con lo cual puedes poner
for
muchas
density and
conectadas.
integration to get performance scaling. Now, a key step in realizing that vision was our training tile. Not only can we integrate 25 dies at extremely high bandwidth, but we can scale that to any number of additional tiles by just connecting them together.
¿A qué hora
Now, last
presentan el
year,
iPhone 14?
we showcased our first functional training tile. And at that time, we already had workloads running on it. And since then, the team here has been working hard and diligently to deploy this at scale. Now, we've made amazing progress and had a lot of milestones along the way. And of course, we've had a lot of unexpected challenges.
Gracias, Marcelo. Gracias por el apoyo. Espero que no me haga mal.
Now, pushing density for performance presents all new challenges. One area is power delivery. Here, we need to deliver the power to our compute die, and this directly impacts our top-line compute performance. But we need to do this at unprecedented
Deja al pobre Marcelo, coño.
We need to be able to match our die pitch with a power density of almost 1 amp per millimeter squared. And because of the extreme integration, this needs to be a multi-tiered vertical power solution. And because there's a complex heterogeneous material stack-up, we have to carefully manage the material transition, especially CTE. Now, why does the coefficient of thermal expansion matter in this case? CTE is a fundamental material property. And if it's not carefully managed, that stack-up would literally rip itself apart. So we started this effort by working with vendors to develop this power solution. But we realized that we actually had to develop this in-house. Now, to balance schedule and risk, we built quick iterations to support both our system bring-up and software development, and also to find the optimal design and stack-up that would meet our final production goals. And in the end,
CT, no, creo que se referían al coeficiente de cómo afecta el calor, entiendo, no sé si al propio material o el tema de dilatación por calor que puede hacer que pase lo que se veía en la carretera, ¿no? Como toda reventada, no sé si va por ahí. Entiendo que sí.
Now, we did have unexpected challenges along the way. Here's an example where we pushed the boundaries of integration that led to component failures. This started when we scaled up to larger and longer workloads, and then intermittently, a single site on a tile would fail. Now, they started out as recoverable failures, but as we pushed to much higher and higher power, these would become permanent failures. Now, to understand this failure, you have to understand why and how we build our power modules. Solving density at every level is the cornerstone of actually achieving our system performance. Now, because our XY plane is used for high bandwidth communication, everything else must be stacked vertically. This means all other components other than our die must be integrated into our power modules. Now, that includes our clock and our power supplies and also our system controllers. Now, in this case, the failures were due to losing clock output from our oscillators. And after an extensive debug,
seguimos viendo el voltage, la historia esta, ¿no? De control del voltaje. Yo aquí esta parte me interesa, pero no manejo tanto, así que me basaré en ver dibujitos.
And often not affected by power circuits. But because we needed to achieve this level of integration, these oscillators need to be placed in very close proximity. Now, due to our switching frequency and then the vibration resonance created, it caused out-of-plane vibration on our MEMS oscillator that caused it to crack. Now, the solution to this problem is a multi-prong approach. We can reduce the vibration by using soft terminal caps. We can update our MEMS part with a lower Q factor for the out-of-plane direction. And we can also update our switching frequency to push the resonance further away from these sensitive bands. Now, in addition to the density at the system level, we've been making a lot of progress at the infrastructure level. We knew that we had to re-examine every aspect of the data center infrastructure in order to support our unprecedented power and cooling density. We brought in a fully custom designed CDU to support Dojo's dense cooling requirements. And the amazing part is we're able to do this at a fraction of the cost versus buying off the shelf and modifying it. And since our Dojo cabinet integrates enough power and cooling to match an entire row of standard IT racks, we need to carefully design our cabinet and infrastructure together. And we've already gone through several iterations of this cabinet to optimize this.
Sigo
Earlier
despierto,
this year,
tranquilos.
we
Sigo
started
vivo.
load testing our power and cooling infrastructure. And we were able to push it over 2 megawatts before we tripped our substation and got a call from the city. Yeah. Now, last year, we introduced only a couple of components of our system, the custom D1 die and the training tile. But we teased the exapod as our end goal. We'll walk through the remaining parts of our system that are required to build out this exapod. Now, the system tray is a key part of realizing
Mirad, cada
our
una de
vision of a
esas
single accelerator.
de esos cuadraditos
It
que se ven
enables us to
es una de estas tiles de entrenamiento, ¿no? Lo que nos estaban
not
explicando.
only within the cabinet, but between cabinets. We can connect these tiles at very tight spacing across the entire accelerator, and this is how we achieve our uniform communication. This is a laminated bus bar that allows us to integrate
Gracias, Alan.
very high power.
Salió tartamudeando, pero bueno, es como suele salir siempre, ¿eh? Su forma de hablar y está guay.
It's 75
Me gusta más ese rollo que el rollo
and supports 6 tiles at
prefabricado y
135
enlatado.
kilograms. This is the equivalent of 3
Divaga
to
un poco,
4
eso sí.
fully loaded high-performance racks. Next, we need to feed data to the training tiles. This is where we've developed the Dojo interface processor. It provides our system with high bandwidth DRAM to stage our training data. And it provides full memory bandwidth to our training tiles using TTP, our custom protocol that we use to communicate.
Dojo es el nombre de su superordenador
It also has high-speed Ethernet that helps us extend
con el que
this
están
custom
entrenando
protocol
todos
over
sus
standard
modelos.
Ethernet. And we provide native hardware support for this with little to no software overhead. And lastly, we can connect to it through a standard Gen 4 PCIe interface. Now, we pair 20 of these cards per tray, and that gives us 640 gigabytes of high bandwidth DRAM. And this provides our disaggregated memory layer for our training tiles. These cards are our high bandwidth ingest path, both through PCIe and Ethernet. They also provide a high radix Z connectivity path that allows shortcuts across our large Dojo accelerator. Now, we actually integrate the host directly underneath our system tray. These hosts provide our ingest processing and connect to our interface processors through PCIe. These hosts can provide hardware video decoder support for video-based training. And our user
Básicamente te
applications
están
land
contando
on these
cómo
hosts
está montado su
we
superordenador
can provide them with the standard x86 Linux
a partir de sus partes, ¿no? Estamos viendo uno de los módulos. Esta es una de las cabinas y ahora pum, 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 pum. Con eso ya tenemos una cabina del Dojo. ¿Cuántas has metido? 3, ¿no? Sería ya 18 tiles, 18 baldosas.
Now, by focusing on density at every level, we can
Fijaos
realize the
cuántas hay.
vision of a single accelerator. Now, starting with the uniform nodes on our custom D1 die, we can connect them together in our fully integrated training tile, and then finally, seamlessly connecting them across cabinet boundaries to form our Dojo
Vámonos.
accelerator.
Es bonito, ¿eh?
And altogether, we can house 2 full accelerators
Y esto
in
es
our
el exapod.
exapod for a combined 1 exaflop of ML compute. Now,
Un
altogether, this
exaflop
amount of
de
technology
computación de machine
and
learning.
integration has only ever been done a couple of times in the history of compute. Next, we'll see how software can leverage this to accelerate their performance.
Thanks, Bill. My name is Rajiv, and I'm going to talk some numbers.
Números.
So our software stack begins with the PyTorch extension that speaks to our commitment to run standard PyTorch models out of the box.
Ahí, PyTorch.
We're going to talk more about our JIT compiler and the ingest pipeline that feeds the hardware with data. Abstraction performance is TOPS times utilization times accelerator occupancy. We've seen how the hardware provides peak performance. It's the job of the compiler to extract utilization from the hardware while code is running on it. And it's the job of the ingest pipeline to make sure that data can be fed at a throughput high enough for the hardware to not ever starve. So let's talk about why communication-bound models are difficult to scale. But before that, let's look at why ResNet 50-like models are easier to scale. You start off with a single accelerator, run the forward and backward passes, followed by the optimizer. Then to scale this up, you run multiple copies of this on multiple accelerators. And while the gradients produced by the backward pass do need to be reduced, and this introduces some communication, this can be done pipeline with the backward pass. This setup scales fairly well, almost linearly. For models with much larger activations, we run into a
Nos está enseñando, bueno, diferentes tipos de modelos de Machine Learning. La ResNet 50, como en sus pasos del forward, el backward, el gradient descent y la optimización, pues cómo escala en la infraestructura que han montado, ¿no? Antes, a más modelos, pues va lineal el coste. Ahora están hablando de grandes modelos de visión.
And while there are ways to get around this, they usually involve tedious manual work best suited for a compiler. And ultimately, there's no skirting around the fact that if your state does not fit in a single accelerator, you can be communication bound. And even with significant efforts from our ML engineers, we see such models don't scale linearly.
Oh.
The DOJO system was built to make such models work at high utilization. The high-density integration was built to not only accelerate the compute-bound portions of a model, but also the latency-bound portions, like a batch norm, or the bandwidth-bound portions, like a gradient all reduce or a parameter all gather.
Estamos en el punto de que ya hay casi igual número de personas, 1263, que número de likes, que son 1272. Estamos a la par. De dinero no. Cuando lleguemos a 1.200 euros, cierro directo. De momento vamos por 50. No está mal.
Freeing the users from having to worry about the internal details of execution. And it's the job of the compiler to maintain this abstraction. Fine-grained synchronization primitives and uniform low latency makes it easy to accelerate all forms of parallelism across integration boundaries. Tensors are usually stored sharded in SRAM and replicated just in time for layers execution. We depend on the high DOJO bandwidth to hide this replication time. Tensor replication and other data transfers are overlapped with compute, and the compiler can also recompute layers when it's profitable to do so. We expect most models to work out of the box.
Stable diffusion.
We took the recently released Stable Diffusion model and got it running on DOJO in minutes.
Out
of the box, the compiler was able to map it in a model parallel manner on 25 DOJO dies. Here are some pictures of a Cybertruck on Mars generated by Stable Diffusion running on DOJO.
Mira, aquí tenéis otra imagen de Stable Diffusion. Musk. O Elon
Looks like it
CSV.
still has some ways to go before matching the Tesla design studio team. So we've talked about how communication bottlenecks can hamper scalability. Perhaps an acid test of a compiler and the underlying hardware is executing a cross-die batch norm layer. Like mentioned before, this can be a serial bottleneck. So the communication phase of a batch norm begins with nodes computing their local mean and standard deviation.
Parece de Alimini, sí, la verdad que los resultados que han sacado no eran muy buenos.
Then broadcasting these values back, and then they resume their work in parallel. So what would an ideal batch norm look like on 25 DOJO dies? Let's say the previous layers activations are already split across dies. We would expect the 350 nodes on each die to coordinate and produce die local mean and standard deviation values. Ideally, these would get further reduced with the final value ending somewhere towards the middle of the tile. We would then hope to see a broadcast of this value radiating from the center. Let's see how the compiler actually executes a real batch norm operation across 25 dies. The communication trees were extracted from the compiler, and the timing is from a real hardware run.
¿Cómo hablo de los créditos de NVIDIA para los cursos? Todavía no os he escrito, pero lo haré esta semana. Sí, que entiendo que eres uno de los ganadores, ¿no? Está pendiente todavía para escribiros.
followed by global reduction towards the middle of the tie, then the reduced value broadcast radiating from the middle, accelerated by the hardware's broadcast facility.
Hay
This
mucho
operation
murmullo,
takes only 5 microseconds on 25 Dojo dice. The same operation takes 150 microseconds on 24 GPUs. This is an orders of magnitude improvement over GPUs. And while we talked about an all-reduced operation in
La
the
comparación, ¿no?, de 25 sistemas de los suyos frente a 24 GPUs.
apply to all other communication primitives. And these primitives are essential
Estas son las
for
ventajas
large-scale
de haber diseñado sus propios
So how about
procesadores.
full model performance? So while we think that the ResNet 50 is not a good representation of real-world Tesla workloads, it is a standard benchmark, so let's start there. We are already able to match the A100 die for die. However, perhaps a hint of Dojo's capabilities is that we're able to hit this number with just a batch of 8 per die. But Dojo was really built to tackle larger, complex models. So when we set out to tackle real-world workloads, we looked at the usage patterns of our current GPU cluster. And 2 models stood out: the auto-labeling networks, a class of offline models that are used to generate ground truth, and the occupancy networks that you heard about. The auto-labeling networks are large models that have high arithmetic intensity, while the occupancy networks can be ingest-bound. We chose these models because together they account for a large chunk of our current GPU cluster usage, and they would challenge the system in different ways. So how did we do on these 2 networks? The results we're about to see were measured on multi-die systems for both the GPU and Dojo, but normalized to
Están comparando con los modelos que nos han enseñado antes, pues cuál es el rendimiento en GPU y cuál es el rendimiento en su sistema Dojo, ¿no?
On our production hardware with our newer VRMs, that translates to doubling the throughput of an A100. And our model showed that with some key compiler optimizations, we could get to more than 3x the performance of an A100.
Pues está, ¿no? Consiguen más del triple con todas las... en el caso de los modelos de autoetiquetado consiguen más del triple con todas las mejoras de hardware y el compilador. Me los quita muy rápido. Y en el otro modelo, que no sé de cuál era, pero creo que es el de Occupancy, más de 4 veces el rendimiento que se consigue con una GPU a 100. Entonces está bastante bien. Esa es la ventaja, ¿no? Lo que entiendo que estaban buscando con la creación de su sistema.
1, 2, 3, 4, 5, and 6 GPU boxes with just a single Dojo tile.
Ahí está. 5 cajas de GPUs equivalen a una tile. Y que cada una de esas tiles cuestan menos que esas 6 GPUs. O que cada una de las GPUs, ¿no? Wow. Esto sí está bastante guapo. Porque al final con eso agilizas un montón tu flujo de trabajo. Porque puedes entrenar más rápido, puedes simular más rápido, puedes entrenar más modelos, puedes escalar, puedes meterle más datos.
The row is mostly white space where the hardware is just waiting for data. With our dense ML compute, Dojo hosts effectively have 10x more ML compute than the GPU hosts. The data loaders running on this one host simply couldn't keep up with all that ML hardware. So to solve our data loader scalability issues, we knew we had to get over the limit of this single host. The Tesla transport protocol moves data seamlessly across hosts, tiles, and ingest processors. So we extended the Tesla transport protocol to work over Ethernet. We then built the Dojo network interface card, the DNIC, to leverage TTP over Ethernet. This allows any host with a DNIC card to be able to DMA to and from other TTP endpoints. So we started with the Dojo mesh, then we added a tier of data loading hosts equipped with the DNIC card. We connected these hosts to the mesh via an Ethernet switch.
Estoy en un punto ya que esto me está costando, O sea, ya estoy pensando en la comodidad de mi cama, pero bueno. Vamos a aguantar, vamos a aguantar. Mandadme apoyo, chicos. Apuntaladme.
Occupancy went from 4% to 97%. So the data loading sections have reduced.
Algo, ¿vale? Han explicado algo.
The data loading sections have reduced drastically, and the ML hardware is kept busy. We actually expect this number to go to 100% pretty soon. After these changes went in, we saw the full expected speed up from the PyTorch layer, and we were back in business. So we started with hardware design that breaks through traditional integration boundaries in service of our vision of a single giant accelerator. We've seen how the compiler and ingest layers build on top of that hardware. So after proving our performance on these complex real-world networks, we knew what our first large-scale deployment would target. Our high arithmetic intensity auto-labeling network.
Lo guapo es que luego toda esta este conocimiento, toda esta infraestructura, todo este know-how se puede mover a otras de las empresas que tiene Elon Musk, ¿no? Estabais comentando Neuralink y todas estas cosas. Se pueden beneficiar, o SpaceX me imagino que para el tema de simulación y cosas utilizarán esta infraestructura, ¿no? Al final todo queda dentro de la misma persona. El primer Hexapod todavía no lo han construido. Qué fuerte. El primer Hexapod estará para el primer quarter de 2023 y quieren construir 7 Hexapods. Qué guay. Justo detrás del muro van a construir ahí 7 de estos superordenadores. Y ahí está, mira una de las cabinas para que le echéis un ojo. Ahí está, ahí podéis poner chuletillas, chorizos, todo lo que queráis. Y te lo cocinan súper bien. ¿Cuánta energía consume? Toda. No lo han dicho, creo. We believe that we can get another 10x improvement with our next generation hardware. ¿Para qué son esos ordenadores? Pues todos los modelos que hemos visto antes de autoetiquetado, de entrenamiento, todos los modelos que van dentro del coche se tienen que entrenar y todos los datos se tienen que etiquetar y eso requiere de una enorme cantidad de computación. O sea, todo lo que hemos visto del mapa de San Francisco simulado, todo eso hace falta mucha computación. ¿Dónde sacas eso? Pues de este Hexapod. Lo han dicho, ¿no? Cuando tengan construido el primer cabinet, podrán tener un doble de rendimiento en el etiquetado de datos. Y ahora van a empezar con preguntas. Aquí yo ya capturamos las 3-4 primeras preguntas y yo aquí cierro porque aquí luego desfasan. ¿Os ha gustado? ¿Os ha molado? ¿Coincidís conmigo que esta es de las ponencias más técnicas de toda la industria, las de Tesla? Y me flipa que lo sea.
Most people have no idea that Tesla is arguably the leader in real-world AI hardware and software, and that we're building what is arguably the first, the most radical computer architecture since the Cray 1 supercomputer. And I think if you're interested in developing some of the most advanced technology in the world that's going to really affect the world in a positive way, Tesla's the place to be. So yeah, let's fire away with some questions. I think there's a mic at the front and a mic at the back.
Fijaos la gente, los ingenieros que han participado, gente súper joven. Está guay, o sea, gente súper joven.
Hi, thank you very much. I was impressed here. Yeah. I was impressed very much by Optimus, but I wonder why tendon-driven, the hand? Why did you choose a tendon-driven approach for the hand? Because tendons are not very durable. And why spring-loaded?
Del tema de las articulaciones de Optimus.
When it comes to any type of actuation scheme, there's trade-offs between, whether or not it's a tendon-driven system or some type of linkage-based system.
Just keep the mic close to your mouth.
A little bit closer.
Yeah.
Hear me? Cool.
Yeah.
So yeah, the main reason why we went for a tendon-based system is that, first we actually investigated some synthetic tendons, but we found that metallic Bowden cables are, a lot stronger. One of the advantages of these cables is that it's very good for part reduction. We do want to make a lot of these hands, so having a bunch of parts, a bunch of small linkages ends up being a problem when you're making a lot of something. One of the big reasons that tendons are better than linkages in a sense is that you can be anti-backlash. So anti-backlash essentially allows you to not have any gaps or stuttery motion in your fingers. Spring-loaded, mainly what spring-loaded allows us to do is allows us to have active opening. So instead of having to have two actuators to drive the fingers closed and then open,
bueno, yo esta parte no controlo, pero bueno, creo que ha preguntado por el tema de los actuadores porque usan muelles, ¿no? Y el tío le ha dicho que les permite pues que haya una respuesta, o sea que no tengas que tener un actuador para cerrar y otro para abrir, sino que hay un retroceso automático por el uso del muelle.
So there's a lot of ways to solve the various problems of a humanoid robot, we're probably not barking up the right tree on all the technical solutions. And I should say that we're open to evolving the technical solutions that you see here over time. They're not locked in stone. But we have to pick something, and we want to pick something that's going to allow us to produce the robot as quickly as possible and have it, like I said, be useful as quickly as possible. We're trying to follow the goal of fastest path to a useful robot that can be made at volume. And we're going to test the robot internally at Tesla in our factory, and just see like how useful is it, because you have to have you've got to close the loop on reality to confirm that the robot is in fact useful, yeah, so we're just going to use it to build things, and we're confident we can do that with the hand that we have currently designed, but for sure there'll be hand version 2, version 3, and we may change the architecture quite significantly over time.
A ver, otra pregunta.
The Optimus robot is really impressive. You did a great job. Bipedal robots are really difficult. But what I noticed might be missing from your plan is to acknowledge the utility of the human spirit, and I'm wondering if Optimus will ever get a personality and be able to laugh at our jokes while it folds our clothes.
Yeah, absolutely. I think we want to have really fun versions of Optimus.
Me ha preguntado la chica que cuándo se van a poder descojonar los robots de nosotros, digo con nosotros. Es muy fácil, o sea, a día de hoy está mucho más desarrollada la parte intelectual, es decir, tener un GPT-3, tener un modelo que te mire, te pueda hablar, te pueda dar conversación, eso lo tenemos más desarrollado que lo que es la parte mecánica del robot.
Actuators figured out, then you can actually, put all sorts of costumes, I guess, on the robot. I mean, you can make the robot look. You can skin the robot in many different ways, I'm sure people will find very interesting ways to versions of Optimus. So.
Thanks for the great presentation. I wanted to know if there was an equivalent to interventions in Optimus. It seems like labeling through moments where humans disagree with what's going on is important, and in a humanoid robot, that might be also a desirable source of information.
Interesante. La pregunta en este caso ha sido el sistema, creo que va por ahí, ¿no? El sistema Autopilot, cuando es de conducción, ellos tienen una cosa interesante, y es que si el conductor está usando Autopilot y de repente hay un problema y el coche se está yendo fuera de carretera, el conductor coge el volante y corrige. En ese momento generas una señal humana de corrección de hey, aquí el coche se ha equivocado. Ese sistema de intervención humana para avisar de hey, esto está mal, ¿cuál sería la versión equiparable, ¿no? En el robot humanoide, es lo que ha preguntado.
Yeah, I think we'll have ways to remote operate the robot and intervene when it does something bad, especially when we are training the robot and bringing it up. And hopefully we design it in a way that we can stop the robot from, if it's going to hit something, we can just like hold it and then it'll stop. It won't crush your hand or something. And those are all intervention data Yeah, and we can learn a lot from our simulation systems too, where we can check for collisions and supervise that those are bad actions.
Yeah, I mean, so Optimus.
Básicamente ha dicho, bueno, que implementarán sistemas de que cuando lo pares, lo cojas, lo varíes su estado respecto a la simulación, pues lo detectará como una señal.
We want over time for it to be, you know, an android, the kind of android that you've seen in sci-fi movies, like Star Trek, The Next Generation, like Data. But obviously, we could program the robot to be less robot-like and more friendly, and you know, it can obviously learn to emulate humans and feel very natural. So as AI in general improves, we can add that to the robot, and you know, it should be obviously able to do simple instructions or even intuit what it is that you want. So you could give it a high-level instruction, and then it can break that down into a series of actions and take those actions.
Hi. Yeah, it's exciting to think that with the Optimus, you will think that you can achieve orders of magnitude of improvement in economic output. That's really exciting. And when Tesla started, the mission was to accelerate the advent of renewable energy or sustainable transport. So with the Optimus, do you still see that mission being the mission statement of Tesla, or is it going to be updated with, you know, mission to accelerate the advent of, I don't know, infinite abundance or limitless economy?
Está preguntando si la misión de Tesla ha cambiado.
Strictly speaking, Optimus is not strictly speaking directly in line with accelerating sustainable energy. You know, to the degree that it is more efficient at getting things done than a person, it does, I guess, help with you know, sustainable energy. But I think the mission effectively does somewhat broaden with the advent of Optimus to, you know, I don't know, making the future awesome. So, you know, I think you look at Optimus, and I don't know about you, but I'm excited to see what Optimus will become. And, you know, this is like, you know, if you could, I mean, we can tell, like any given technology, do you want to see what it's like in a year, 2 years, 3 years, 4 years, 5 years, 10? I'd say for sure. You definitely want to see what's happening with Optimus. Whereas, you know, a bunch of other technologies are, you know, sort of plateaued. Won't name names here, but you know, so I think Optimus is going to be incredible in like 5 years, 10 years, like mind-blowing. And I'm really interested to see that happen, and I hope you are too.
Vale.
I have a quick question here. I'm Justin, and I was wondering, like, are you planning to extend like conversational capabilities for the robot? And my second follow-up question to that is, what's like the end goal? What's the end goal with Optimus?
Yeah, Optimus would definitely have conversational capabilities. You'd be able to talk to it and have a conversation, and it would feel quite natural. So, from an end goal standpoint, I don't know. I think it's going to keep evolving, and I'm not sure where it ends up, but someplace interesting for sure. You know, we always have to be careful about the, you know, don't go down the Terminator path. That's a, you know, I thought maybe we should start off with a video of like the Terminator starting off with the, you know, skull crushing, but that might be, you know, people might take that too seriously. So, you know, we do want Optimus to be safe, so we are designing in safeguards where you can locally stop the robot, and you know, with like basically a localized control ROM that you can't update over the internet, which I think that's quite important, essential, frankly. So, like a localized stop button, remote control, something like that, that cannot be changed. But I mean, it's definitely going to be interesting. It won't be boring. So.
Vale, vamos a parar aquí, vamos a hacer wrap up, vamos a comentar un poco lo que ha dicho y vamos a ir terminando. A ver, nada, ha sido 2 preguntas centradas en lo de Optimus. La anterior era si la misión corporativa de Tesla había cambiado, porque originalmente con el tema de la conducción autónoma, los vehículos eléctricos y tal, pues su misión era revolucionar, hacer una revolución energética hacia energías renovables y claro, le habían preguntado Optimus dónde encaja dentro de esa lógica, ¿no? Porque lo primero que ha comentado Elon ha sido que a nivel el impacto que va a tener el Tesla Bot, el Optimus en un futuro será a nivel económico, generando abundancia, porque según su criterio pues va a haber un crecimiento de 2 órdenes de magnitud. Entonces, bueno, ha respondido un poco ahí. Su respuesta un poco ha sido decir que bueno, esto seguirá evolucionando y que será interesante de ver cómo va a evolucionar todo esto, a diferencia de otras tecnologías que bueno, han ido aplanándose, su grado de innovación se ha ido parando. Y ha dicho, no quiero decir nombres, y se ha reído como un pícaro. No sé exactamente a qué se estaría refiriendo. No sé si estaba pensando, por ejemplo, en el mercado de la telefonía móvil. Me lo puedo imaginar. O no sé si se refería a otra cosa. O al sector del automóvil tradicional. Y bueno, en la segunda pregunta también le estaban preguntando el tema de bueno, si va a haber capacidades de poder dialogar con el bot, y dónde acabaría, ¿no? ¿Cuál es el objetivo final a dónde se quiere llegar aquí? Y él ha dicho que bueno, que no hay un objetivo final, que simplemente se va a seguir desarrollando y que lo único que hay que tener cuidado es no irse por la línea de el Terminator, que podían haber empezado la charla de hoy con el robot pisando una calavera al estilo de la película de Terminator, pero que a lo mejor eso era demasiado too much. Y yo creo que sí sería too much, porque el robot, al intentar pisarla, seguramente se hubiera caído al suelo. No lo vamos a negar. Pero en general yo tengo que decir que me ha gustado. Me ha gustado bastante. Respecto a mi sensación del año pasado, que fue un poco el momento Tesla Bot fue... parece que ha hecho una fumada, un poco de fuegos artificiales al estilo Elon, para tener un poco a la gente enganchada a lo próximo que van a ir desarrollando, y cada año veremos un poco de robot por aquí y por allá, y ese va a ser como el gimmick de los próximos años para seguir vendiendo coches. Pero sinceramente la sensación que me ha dado es que están apostando muy fuerte por esto. O sea, han creado, 1/3 de la charla ha sido hablando del Tesla Bot, de Optimus. Y de cara a lo que han trabajado desde el año pasado hasta ahora, o lo que enseñaron el año pasado hasta ahora, sinceramente han avanzado bastante. ¿Por qué me parece interesante? Porque es cierto, y muchos lo decís, que a nivel de robótica no está donde, por ejemplo, está Boston Dynamics. Y es cierto que Boston Dynamics tiene unos robots que son espectaculares, pero no son robots, por ejemplo Atlas, ¿no? Que sería su robot bípedo humanoide, no está en la misma liga que lo que están haciendo ellos, porque ellos están buscando un robot que pueda ser comercializable, que sea barato, que pueda realmente trasladarse a un mercado, venderse a empresas, etc. Entonces, Atlas, por muy impresionante que sea, es una edición limitada, son versiones muy limitadas que funcionan muy bien, pero dentro del laboratorio de Boston Dynamics. Y lo importante, no tienen inteligencia artificial, o no tienen algoritmos de deep learning como los que acostumbramos a ver nosotros aquí en el canal de YouTube. Entonces me parece muy interesante que Tesla sí tiene este know-how que ya han desplegado los coches, de no solo hacemos máquinas como los coches de Tesla que tienen un hardware impresionante, sino que también lo integran muy bien con su software, con su todo lo que hemos visto hoy, con sus modelos de inteligencia artificial, con sus procesos de carga de datos. Y parece evidente, por lo que se está viendo, que hay mucha transferencia de conocimiento que puede haber entre ambos sectores, ¿no? Al final el autopilot, la forma de recopilar datos, de etiquetar datos, todo lo que hemos visto, ¿no? El generar rutas que están codificadas como tokens dentro de un modelo autorregresivo de deep learning, todo eso también se puede trasladar a la lógica de funcionamiento del Tesla Bot. Entonces, está guay. Está guay, necesitamos más gente, y esto le va a venir también a Boston Dynamics, que se van a poner las pilas en productivizar su línea de robots para que puedan competir con Tesla. Y es interesante porque al final están reactivando un mercado que es muy loco, que estamos hablando de robots, amigos, que ¿por qué de repente el futuro se parece al futuro? O sea, tenemos la inteligencia artificial haciendo cosas muy locas, tenemos ahora gente produciendo robots, no sé qué va a ser lo próximo, pero el futuro se está dibujando y está llegando a pasos más rápidos de lo que creíamos. Entonces, la buena noticia es que desde hace mucho tiempo ya tenemos el software, la inteligencia hecha. O sea, lo que puede hacer ahora mismo a nivel de inteligencia artificial un ordenador es impresionante. ¿Cuál es el siguiente paso? El embodiment, el meterlo dentro de un robot a esta inteligencia artificial y ver cómo puede interactuar con el mundo, cómo nos puede aportar, cómo puede generar este valor. En ese sentido, pues vamos a ver qué puede aportar Optimus y al menos tenemos una cosa interesante de cara a los próximos años. Así que a Tito Elon, pues en este sentido, pa'lante con sus locuras, ¿no? Al final, Elon plantea su locura, no deja de ser este millonario excéntrico que a veces nos sorprende con esta faceta de ingeniero y otras veces se pone a divagar a lo loco, pero lo importante aquí no es eso, sino todo el equipo de gente que consigue atraer a su visión, ¿no? Que esa es la parte quizás que hay que reconocerle, que es capaz de atraer a mucho talento, y este evento pues no deja de ser un poco más de lo mismo, ¿no? Atraer talento para su empresa. Por eso ha sido un evento tan técnico. Nada más, chicos, agradeceros que estéis por aquí, que hayáis venido, que hayáis acudido a este directo. No sé si habéis aprendido cositas, no sé si os lo habéis pasado bien o si ha sido demasiado turra, demasiado coñazo, si esperabais más o menos, pero bueno, yo me lo he pasado muy bien, como siempre. A mí estos directos me gustan muchísimo y además os habéis portado genial, habéis estado aportando también ahí en el chat. Y nada, bueno, este directo se va a quedar resubido si lo queréis volver a repasar, si lo queréis compartir, que eso siempre es importantísimo. Y tenéis otros directos y otros vídeos en el canal. Están saliendo un montón de cosas súper interesantes, así que si no estáis suscritos al canal, suscribiros, porque de verdad que están pasando demasiadas cosas en muy poquito tiempo y os lo estaré contando en los próximos vídeos y directos. Y poco más, nada, que nos vemos en el próximo vídeo. Si os interesa todo este mundillo, si queréis aprender más de todo esto, si queréis empezar a introduciros a nivel usuario, a nivel de, pues a lo mejor tenéis una empresa o algo en el mundo de la inteligencia artificial, recordad que tenéis abajo información en la caja de descripción del máster del Instituto de Inteligencia Artificial, que empieza una nueva edición este mes de octubre, que con el descuento, con el código de descuento de DOTCSV 300, pues tenéis 300 euros de descuento sobre el precio de la matrícula, ¿vale? Un máster que además está llevado por Andrés Torrubia y bueno, un grupo de profesores que son excelentes, y además también estoy yo ahí colaborando y un montón de expertos que conoceréis, ¿vale? Nada más, chicos, chicas, son las 6 de la mañana, un servidor se va a dormir, creo que no se ha notado para nada que me estoy cayendo de sueño y que os quiero mucho. Vale, hasta el próximo vídeo. Chao, chao.